1 million miles from the world of its makers, a machine the size of a tennis court drifts through the silent dark. It is rewriting the very first chapters of cosmic history. It has found galaxies that ignited only 290 million years after the Big Bang. It has witnessed black holes heavier than the star cities they inhabit. It has captured the final, violent light of stars exploding at the edge of time itself. This is a chronicle told in photons that have traveled for 13 billion years, a journey across an expanding void to finally reach a golden mirror. These are discoveries that challenge the fundamental laws of our understanding. This sentinel is the James Webb Space Telescope, the culmination of 20 years of human ingenuity and a $10 billion wager on our own curiosity. In the vacuum of space, its grenelles, each forged from beryllium and coated in a whisper-thin layer of gold, engineered to catch the faintest, oldest light in creation. Unlike its predecessor, Hubble, this telescope does not orbit our planet. It circles a phantom point in space, a place of perfect gravitational balance known as the second Lagrange point. Here, perpetually shielded from the sun by a 5-layered shield the size of a playing court, with a protective factor of over 1 million, Webb stares into the infrared. It must see in this invisible spectrum because the universe is expanding. The light from the most distant, ancient galaxies stretches as it crosses the cosmic fabric. Wavelengths that began their journey as visible blue and ultraviolet are pulled over billions of years into the deep infrared. Hubble's eyes were blind to this primordial glow. Webb sees what was once forever hidden. It was launched on Christmas Day, 2021. For 6 agonizing months, engineers watched from a world away as the machine performed its intricate dance of deployment. 1,044 individual procedures had to execute in perfect sequence. A single failure would have doomed the entire mission to become a $10 billion ghost. Every panel unfolded without error. Every instrument activated flawlessly. Then, it opened its golden eye and looked deeper into time than any machine in history. Each of its observations is an act of time travel. To see a galaxy 1 billion light-years away is to witness that galaxy as it existed 1 billion years ago. Webb pushes this principle to its absolute limit, capturing photons that began their journey when the universe was less than 5% of its current age. They appear as faint red smudges against the black, these nascent galaxies. Their light has been traveling for more than 13 billion years. We are not merely observing distant objects, we are watching the birth of the cosmos. Scientists had believed they knew what this Cauchy theorized was too young for anything complex to have formed. In its very first week of operation, Webb shattered those expectations. It revealed a universe that was shockingly mature, intricate, and brilliant, far sooner than any model had ever predicted. The light from these first galaxies carried a message across an expanding void. It tells us not only what the universe was, but what we are, the momentary consciousness of a cosmos, finally able to look back and behold its own magnificent and mysterious beginning. From the silent depths of space, the images arrived, and they were wrong. They were too large, too brilliant, too mature. Some had already assembled into massive structures, cosmic architecture that should have required billions of years to construct. One astronomer called it completely unanticipated. Another confessed it might break cosmology itself. The standard model of the universe, our fundamental story of creation, had predicted one thing, but the telescope was showing us something entirely different. Every image revealed galaxies that threw decades of theory into question. Every spectrum told a story that did not fit the textbook narrative. What does one do when their finest instrument reveals the impossible? You keep looking. And what it found next was stranger still. It appeared as little more than a tiny red dot, lost in the tapestry of Webb's first deep-field images. Astronomers assigned it a catalog number and moved on. But then, someone ran the calculations. The light from this single point had been stretched by the expansion of the universe by a factor of 15. It had traveled from a time just 290 million years after the Big Bang. The universe is 13.8 billion years old. This galaxy had formed when reality was only 2% of its current age. They call it JADES. For months, scientists stared at the data, convinced of an error. They rechecked every variable, every assumption, every line of code, but the measurements held firm. This was not a mistake. JADES spans more than 1,600 light-years in diameter, glowing with the furious light of countless forming stars. It is so bright, Webb could have detected it even if it were 10 times fainter. The implication is staggering. Countless other galaxies from this primordial era are out there, waiting in the dark to be discovered. Perhaps even galaxies that formed earlier, in the first 200 million years after creation. Herein lies the problem. Standard cosmology dictates that galaxies grow slowly. They begin as humble clumps of matter, coalescing within halos of dark matter. Gravity patiently pulls in gas. Stars ignite. Over billions of years, they merge and swell into the grand spirals we know today. And far too large for its age. Our best computer simulations predicted that the first galaxies would be dim, chaotic, and small. JADES is none of these things. Its light radiates from young stars, not from the brilliant accretion disk of a supermassive black hole. This makes the puzzle even deeper. A black hole can generate immense brightness from a tiny region, but star formation requires time, a resource the infant universe should not have had in such abundance. Across the early cosmos, other galaxies echoed the same impossible pattern. One scientist described it as finding a fully grown adult where you expected to see a newborn infant. The universe, by our understanding, simply did not have enough time for these structures to form through conventional means. In the face of this cosmic paradox, new ideas must take root. Perhaps galaxy formation was a far more violent and rapid process in the early universe. Perhaps the first stars ignited with an efficiency we can barely imagine. Or maybe the invisible scaffolds of dark matter collapsed faster than our models allow. We built an eye to gaze back at the beginning, hoping to confirm the story we told ourselves about the universe. Instead, it showed us that the book of creation is still being written, and its opening chapters are wilder, more brilliant, and far more mysterious than we ever dared to believe. And yet, these explanations, however elegant, fall short. The observations remain too extreme. Another path leads back to the very beginning, to what astronomers call initial conditions. Perhaps the dawn of time was not a smooth, uniform event. If the Big Bang scattered matter unevenly, creating pockets of immense density, then galaxies could have ignited there with impossible speed. But this only trades one mystery for another. Why would such regions exist? What primordial process could have carved them from the fabric of the nascent universe? The latest discoveries have extended our view into cosmic history by 40% in a mere 18 months of observation. With every new galaxy pulled from the depths of time, another piece is added to a grand cosmic puzzle whose pieces refuse to align. One researcher confessed they built these great machines not to confirm the paradigm, but to break it. They simply did not know how it would break. And then, the Webb Telescope found something else. Something that made the problem of massive galaxies seem trivial. In the universe we know, there is a fundamental rule. For every 10,000 solar masses of stars that constitute a galaxy, there exists roughly one solar mass in the supermassive black hole at its heart. This ratio is a constant, a cosmic law that holds true wherever we look. The Milky Way obeys it. Our galactic neighbors obey it. Until now. Astronomers focused on a galaxy from a time when the cosmos was only 570 million years old. They measured the mass of its stars. Then, they measured the black hole enthroned at its center. The numbers were incoherent. The black hole accounted for 10% of the galaxy's entire stellar mass. For every 10 suns worth of stars, there was 1 sun's worth of black hole. This single object shattered the cosmic law by a factor of 1,000. Scientists call it an overmassive black hole, a term that barely contains the sheer impossibility of the finding. It is an anatomical absurdity. Imagine a human heart that weighed 1/10 as much as the entire body. This is the scale of the disproportion. The black hole is not merely a central anchor. It is a gravitational titan that dominates its entire system. Webb has since found dozens of these anomalies. In the telescope's deepest images, they appear as faint red dots. The crimson glow is not from stars, but from the fury of matter caught in a final, desperate spiral. As gas accelerates toward the event horizon, it is superheated to millions of degrees, radiating a torrent of energy that outshines the entire host galaxy. This discovery challenges the very bedrock of galactic evolution. In the modern universe, black holes and their galaxies grow in a delicate, synchronous dance. A larger galaxy hosts a larger black hole, always maintaining that sacred ratio of 1 to 10,000. Entire theories were built upon this predictable harmony. But these primordial galaxies tell a different story. Here, the black holes grew first, and they grew ferociously. They achieved monstrous sizes before their host galaxies ever had a chance to fill with stars. One scientist described it as finding an infant with the heart of a giant. The proportions are all wrong. The sequence of creation has been inverted. We are staring into the abyss of the early cosmos, only to find that the rules we thought were universal were perhaps never rules at all. In the cosmic dawn, a profound enigma took shape. Monstrous black holes, millions of times the mass of our sun, loomed in the infant universe. How did they achieve such astonishing mass, so impossibly fast? Two competing narratives emerged from the heart of cosmology. The first is a story of slow, patient growth, born from stellar collapse. From the death throes of the first colossal suns, black holes could be born. These stellar remnants would then begin to feed, relentlessly drawing in the gas and dust and stars that surrounded them. But this is a process bound by time. Even accreting matter at the absolute physical limit, the journey from a single dead star to a million solar mass behemoth in just 500 million years would require conditions of almost unimaginable perfection. The clock of the early cosmos seemed to tick too quickly for such a gradual ascent. This led to a second, more radical theory. Some black holes were simply born big. They did not begin as stars at all. Instead, they were forged in a cataclysm of direct collapse, when vast, primordial clouds of gas, under their own immense gravity, fell inward not to ignite as a generation of stars, but to form a single, monolithic black hole. These seeds would have been immense from their first moment of existence, weighing thousands or even millions of solar masses. They had bypassed the slow, incremental path of stellar evolution entirely. Now, data from the Webb Telescope lends powerful credence to this second story. Observations from the farthest reaches of space and time hint that these giants could not have grown from stellar seeds. There simply was not enough time. They must have started large. Yet the solution to one mystery gave rise to another. What unique and extraordinary conditions could compel a cloud of pure cosmic gas to forswear the birth of stars and instead collapse directly into darkness? The story grows stranger still when we look at where they were found. These primordial titans were not scattered at random across the canvas of the early universe. They occupied a privileged place within the architecture of the cosmos itself. When astronomers mapped the faint, distant galaxies that housed them, seen only as little red dots, they discovered a pattern. The dots clustered together along the cosmic web, the grand-scale structure of the universe, where the placement is a critical clue. More mature, evolved galaxies tend to gather at the dense intersections where these filaments meet. Less developed galaxies are found scattered along the threads themselves. These little red dots, with their overmassive black holes, held specific positions within this celestial tapestry. They were not the largest structures, but they were among the most furiously active, their central engines consuming matter at a ferocious rate. One survey analyzed 7 of these ancient objects, seen as they were when the universe was 12.5 billion years younger than it is today. The results were stunning in their uniformity. All 7 displayed the same impossible ratio, a gargantuan black hole residing within a surprisingly modest galaxy. This was not a collection of cosmic oddities. It appeared to be an entirely distinct population of celestial beings, native to the dawn of time. As these black holes feasted, they unleashed a torrent of energy, a storm of radiation that poured out into their host galaxies. This process, known as feedback, heated the surrounding gas, violently pushing it away. In the modern universe, this feedback acts as a delicate cosmic thermostat, regulating the birth of new stars. But in these fledgling galaxies, the effect may have been overwhelming. The black holes, having achieved immense size so early, may have turned on their hosts, blasting their own galactic nurseries with so much energy that they stunted their growth forever. It is a breathtaking paradox. The very engine of creation at the heart of these galaxies was also the agent of their containment. In the beginning, it seems, the universe forged giants whose very existence prevented their own kingdoms from ever matching their scale. A cosmic drama of creation and suppression played out in the first act of existence. In the cosmic dawn, a great suppression was underway. A galaxy, brimming with potential, was held in a state of arrested development, its stellar nurseries cold and barren. The culprit was a tyrant at its heart, a ravenous black hole whose energetic feedback acted as a relentless gale, blasting away the very gas needed to form new stars. The galaxy was stunted, a kingdom ruled by a monarch that prevented its own subjects from being born. Only much later, after the black hole's fury subsided, could the cosmic gases finally cool, coalesce, and ignite into the brilliant fires of starbirth. Over eons, this slow recovery would gradually restore the balance between a galaxy and its central monster, creating the familiar ratios we observe in the universe today. But this narrative conceals a fundamental paradox, a flaw in the sequence of events. If these colossal black holes form first and sterilize their galactic hosts, from where did the titans themselves arise? They too require an immense diet of gas to grow. If they are the architects of galactic deserts, how did they first acquire the mass to wield such power? One possibility is a brief, violent window of unchecked growth. In this scenario, a black hole is born and immediately enters a phase of voracious consumption, swallowing staggering quantities of gas before its own feedback engine can fully ignite. During this fleeting epoch, it can swell to millions of times the mass of our Sun. Only then does the energy storm erupt, shutting down its own growth and simultaneously halting the formation of stars across the galaxy. The feast is followed by a long, imposed famine. Another theory points to a more brutal path, cosmic cannibalism. In the tightly packed confines of the young universe, galaxies were closer neighbors. Inevitable collisions would bring them together, their central black holes spiraling toward one another in a final gravitational dance. Their merger would instantly forge a far more massive object. A series of such violent unions could rapidly build the supermassive black holes we see in the deepest recesses of time. The Webb Telescope has already captured the faint light of these ancient mergers, lending credence to this chaotic model of creation. Yet, recent observations have added a confounding clue. Some of these impossibly large black holes reside in galaxies that are chemically pristine, almost untouched. The universe's heavy elements, the carbon, the oxygen, the iron, are forged in the hearts of stars and scattered into space when they die. A galaxy rich in stars should be rich in this stellar ash. But these galaxies are not. Their low chemical enrichment suggests very few generations of stars have ever lived and died there. This haunting emptiness points toward a more exotic origin. Perhaps these black holes were not born from the collapse of stars at all, but were forged directly from the raw, unblemished hydrogen and helium of the Big Bang itself. These primordial seeds would not require a pre-existing generation of stars to grow, explaining the startling lack of chemical complexity in their domains. Each spectrum Webb captures adds another brushstroke to this portrait of the early cosmos, revealing a universe that operated by a different set of rules. 350 years ago, in our own galactic neighborhood, a star died a violent death. Its final, brilliant flash raced outward at the speed of light, a ghostly messenger crossing the silent void. In the year 2025, that pulse of ancient radiation finally reached its destination, a placid cloud of interstellar dust and gas. The James Webb Space Telescope was waiting. It watched as the light struck the cloud, not as an impact, but as an illumination from within. The glow it captured was exquisite, revealing the cloud's hidden architecture. What scientists saw resembled the intricate knots and walls of wood grain, tightly packed sheets of material, with structures spanning 400 astronomical units. The light from a long-dead star had become a flashlight, revealing the unseen structure of the space between worlds. In this, we see a reflection of our larger quest, using the ancient light from the edge of time to illuminate the dark origins of everything that followed. The universe is not merely a collection of objects, but a series of events, an unfolding story written in light, and we are only now learning how to read its earliest, most enigmatic chapters. In the vast, silent gulfs between the stars, a hidden architecture has been revealed. Here, at a scale finer than 1/100th of a light year, lies a level of detail no one knew existed within the interstellar medium. Astronomers call the phenomenon a light ek, but its medium is light, and its timescale is cosmic. The flash from a dying star acts as a celestial spotlight, a fleeting pulse of illumination on material that would otherwise drift unseen in the dark. As this wave of light expands outward, it sweeps across progressively more distant veils of dust and gas, creating a moving, ethereal echo that travels through space. The observations were trained not on a star, but on the ghost of one, a region near the supernova remnant Cassiopeia A, the shattered remains of a star that violently exploded in the 1600s. The telescope did not gaze upon the remnant itself. Instead, it focused on the backdrop, on ancient material set aglow by the fury of that long-ago explosion. This illuminated dust and gas has no connection to the star that died. It is simply unrelated cosmic matter that happened to be in the right place at the right time. What it revealed stunned the research team. They had anticipated seeing diffuse, formless clouds, the chaos of the void. Instead, they found order, an intricate structure of nested, organized layers. One scientist described it as an onion, its shells peeling back to reveal an inner complexity. Sheets of material are stacked one upon another in delicate patterns. Some appear sculpted by invisible forces, their dust aligned into parallel formations by magnetic fields threading their way through the cosmos. This discovery fundamentally alters our perception of deep space. The void is not empty. Every cubic meter holds atoms of gas and grains of dust, the raw material of creation. Most of it gathers in colossal clouds, the very nurseries where new stars are born. Understanding their internal structure is the key to understanding this process. Before this, astronomers could only study the outer skins of these clouds. Now, they can peer inside. The newly found structures measure some 400 astronomical units across. For perspective, our entire solar system, out to the distant orbit of Neptune, spans a mere 120 astronomical units. These sheets are several times larger than our whole planetary system, and yet they are but small features within clouds of unimaginable size. Why this order? Why do these materials organize into vast sheets rather than random clumps? Magnetic fields offer a powerful explanation. The interstellar medium is woven with these lines of force, guiding charged particles and dust grains into alignment. Over eons, this celestial magnetism creates elongated, layered structures. The ceaseless turbulence of interstellar gas also plays its part, stirring the material into the complex patterns now seen for the first time. Researchers now believe that most dense, dusty regions in space are built this way on the inside. Every molecular cloud, every star-forming region, likely contains this same layered architecture. We have simply never had the eyes to see it. A new template for the cosmos has been unveiled, a glimpse into the three-dimensional framework of interstellar space, showing us not a void, but a universe of profound and intricate design, waiting in the darkness to be illuminated. A cosmic tapestry reveals itself, woven from the very matter that drifts between the stars. Vast, invisible sheets of gas serve as cosmic rivers, channeling the raw material of creation along unseen pathways. Where these currents intersect, where the gas compresses under its own immense gravity, the conditions become ripe for ignition, the very crucibles where new suns are forged. To understand this architecture is to learn how to predict the next stellar birth. A revolutionary method unlocks this hidden landscape. Using a technique known as light echo, astronomers no longer peer into the darkness alone. They lie in wait for the universe to provide its own illumination, for supernovae or other brilliant, transient events to act as a cosmic flashbulb. As the pulse of light ripples outward, it illuminates the interstellar structures in its path, then reveals. Each echo is a fleeting snapshot, a single frame in the grand motion picture of the galaxy. But in a breathtaking display of cosmic duality, even as one of Webb's eyes gazes upon the local architecture of our galaxy, the other peers across the abyss of time, to the very dawn of creation. On March 14, 2025, a space telescope registered an incandescent scream of gamma rays. The burst, the most violent and energetic event known to science, lasted only a few seconds. Within hours, a global network of ground-based observatories swiveled in unison, racing to capture the fading afterglow. The ancient light they gathered told an extraordinary story. This explosion had occurred when the universe was a mere 730 million years old. The source was a cataclysm, the death of a single, massive star. Stars more than 10 times heavier than our own sun burn with a ferocious intensity, only to die in spectacular violence. When their nuclear fuel is exhausted, the core collapses in less than a second. The star's outer layers, suddenly unsupported, crash inward, rebound against the impossibly dense core, and are blasted out into space. This is a supernova. In the most colossal of stars, the collapse also spawns twin jets of matter, which erupt through the dying star at nearly the speed of light. These jets unleash a focused torrent of gamma rays. If one of these beams happens to be aimed directly at Earth, we witness a gamma ray burst. This is precisely what unfolded on that March morning. Astronomers had seen these events in the distant universe before, but this one set a new record. Its light had been traveling for over 13 billion years. We were witnessing a star explode during the epoch of reionization, the pivotal era when the first stars and galaxies were burning away the primordial fog of neutral hydrogen that had filled the cosmos since the Big Bang. The discovery was no accident. Ground-based telescopes confirmed the extreme distance through spectroscopy. But the most crucial observation came 110 days after the initial burst, when Webb turned its gaze to the fading phantom. By then, the blinding flash was gone. All that remained was the supernova itself, a slower, dimmer echo of the initial violence. Here, Webb performed a feat of astronomical precision. It separated the fading light of the supernova from the far fainter glow of its host galaxy. From our vantage point, the two are an indistinguishable point of light, with the explosion vastly outshining the galaxy that gave it birth. But with its unparalleled sensitivity in the infrared, Webb could resolve the impossible, identifying both the ghost of the explosion and the cradle that had hosted the dying star. In that single point of light, a star's final scream from the edge of time, we find more than just an end. We find a beginning. We see the heavy elements forged in its heart, seeded into a young universe, becoming the building blocks for even, making the universe transparent, and allowing the grand story of structure, of galaxies, of worlds, and of ourselves to finally begin. Across the unfathomable gulf of time, an observation unveiled a ghost from the cosmic dawn, an ancient supernova, a star that had died when the universe was in its infancy, looked remarkably familiar. Astronomers held its fading light against the modern counterpart, a well-documented stellar explosion from the year 1998. The brightness, the signature of its elements, the very rhythm of its decay, they were nearly identical. It was an echo from our own cosmic neighborhood, reverberating across billions of years. This profound consistency offered a deep comfort. It suggested the laws of physics are immutable, that the grand, violent process of stellar death is a constant, written into the fabric of space-time. The way a massive star dies today is the way it has always died. But within this comfort lay a deep puzzle. The early universe was a profoundly different place. Its first stars were born from a pristine gas of almost pure hydrogen and helium. The modern cosmos is enriched, seeded with the heavy elements forged in the hearts of countless stellar generations that came before. This cosmic inheritance, this metallicity, is believed to dictate the life and death of a star. Yet the similarity between the ancient and the modern suggests this inheritance may matter less than we ever imagined. Perhaps the most massive stars, the true chemistry of their birth. The galaxy that hosted this primordial explosion was itself a whisper, a small, faint smudge, barely detectable even with our most powerful instruments. It tells us that in the beginning, the grand work of creation was happening in the humblest of places. These tiny galaxies were the building blocks, destined to collide and merge, eventually forming the sprawling structures we see today. Each of these distant deaths becomes a beacon. For a fleeting moment, the explosion illuminates its surroundings, allowing us to probe the composition and density of the interstellar gas, giving us a direct glimpse into the environment of the early universe. While this ancient death supported our models of how stars evolve, it left a lingering question. Why did an environment so poor in metals not produce a more alien outcome? The death of this single star was a solitary event, a final, brilliant cry in the dark. But elsewhere in that young universe, cosmic titans were not dying alone. They were merging. In a system designated ZS7, existing just 740 million years after the Big Bang, astronomers saw not one, but two brilliant cores, burning with impossible intensity. At first, they questioned if they were witnessing a single galaxy with a bizarre, cloven heart. The answer was written in the spectrum of its light. The data revealed gas moving at tremendous speeds, swirling violently around both points of light. The conclusion was inescapable. These were not stars. They were two colossal black holes, locked in a gravitational dance, on an inexorable course to collision. The early universe was not a quiet nursery, but a crucible. It was a chaotic, violent epoch of brilliant, isolated deaths and the thunderous merger of galactic cores. It was a time when the fundamental rules were being tested, and the very foundations of our own existence were being violently laid. A maelstrom of incandescent gas, moving at velocities of hundreds of kilometers per second, swirls in a gravitational death spiral. This is the unmistakable signature of matter plunging into a black hole. As it accelerates, the gas ignites, reaching millions of degrees and emitting a characteristic spectrum of light, a flare announcing the presence of an actively feeding Leviathan. In the heart of a distant galaxy, known as ZS7, astronomers witnessed this telltale signature not once, but twice. Here, two supermassive black holes were locked in orbit, a discovery representing the earliest such merger ever detected. The two objects are spiraling inexorably inward, destined to collide and combine into a single, more monstrous entity. To witness this cosmic dance required an unprecedented eye. The James Webb Space Telescope's razor-sharp imaging allowed the team to spatially separate the two black holes, revealing them as close but distinct points of light. Where ground-based telescopes would see only a single blurred point, and where prior space-based instruments lacked the infrared sensitivity to pierce the cosmic gloom, only Webb could resolve the system and identify the merger in progress. The discovery has profound implications, striking at the heart of a fundamental cosmic mystery. In the local universe, nearly every large galaxy hosts a central supermassive black hole. But how did these objects grow to weigh millions or even billions of times the mass of our Sun? One proposed mechanism is merging. When two galaxies collide, their central black holes eventually sink to the core of the newly formed system and combine. If such mergers were rare in the early universe, black holes would be forced to grow primarily by consuming gas, a slow, methodical process. Even feeding at the maximum possible rate, a stellar mass black hole would require hundreds of millions of years to achieve supermassive scale. The revelation within ZS7 suggests that in the universe's infancy, growth was not always patient. Finding a merger at cosmic dawn implies they happened frequently enough to dramatically accelerate the formation of these giants. The two black holes in ZS7 are not yet touching. They orbit each other in a tightening embrace, gradually losing energy. This energy bleeds away not as light, but as gravitational waves, ripples in the very fabric of space-time, predicted by Einstein a century ago. As they circle, they broadcast these waves across the cosmos, carrying away orbital energy and shrinking their path. The final, thunderous collision will release a tremendous burst of these waves, a cataclysmic event echoing across billions of light years. While current detectors on Earth are sensitive only to smaller black holes merging in the nearby universe, the next generation of space-based observatories will extend our senses, allowing us to hear the gravitational symphony of supermassive black holes at the highest redshifts. By detecting these echoes from the dawn of time, astronomers can finally calculate the rate of these primordial events. Only then will we know how much of the universe's structure was built through slow accretion, and how much was forged in the violent crucible of cosmic collision. In the first billion years after the Big Bang, the universe was a crucible, a place of violent creation. Within this cosmic dawn, a system known as ZS7 offers a glimpse into the forces that would shape everything to come. Here, two galaxies are locked in a gravitational embrace. Their stars, separated by vast emptiness, rarely touch. But their immense clouds of gas are not so fortunate. They crash together in a cataclysmic shockwave, compressing primordial material until it collapses and ignites in furious bursts of star formation. As the two galaxies bleed into one another, they forge a single, more massive entity. Yet at the heart of this collision, a slower, more inexorable drama unfolds. The central supermassive black holes, the gravitational anchors of their respective galaxies, must shed their cosmic momentum. Over millions of years, they are dragged inward by the gravitational friction of surrounding gas and stars, spiraling closer, until they finally coalesce. The stellar mass of this merging system is familiar, akin to the large Magellanic Cloud that orbits our own Milky Way. But imagine that small companion galaxy containing not one, but two supermassive black holes, each as massive as the one at our galactic center. The gravity of these behemoths would dominate the destiny of every star. This is the reality we are witnessing in ZS7. To find such a merger so early in cosmic history is a revelation. It tells us that the grand processes shaping the universe today were already furiously at work when the cosmos was but a fraction of its current age. But to see these ancient systems is to confront a fundamental challenge. The light from these impossibly distant shores has been traveling for so long. The very fabric of space has expanded beneath it. This cosmic expansion stretches the light, lengthening its wavelength in a phenomenon astronomers call redshift. A redshift of 1 means the light's wavelength has doubled. A redshift of 2 means it has tripled. The light from a galaxy designated Jades arrives with a redshift of 14.32. Its wavelength has been stretched by a factor of 15. What began its journey as fierce ultraviolet radiation from newborn stars arrives at the Webb Telescope as faint infrared heat. The light has been shifted so profoundly, it has become utterly invisible to any instrument not designed to perceive this ghostly glow. To confirm this incredible distance requires a technique of cosmic forensics, spectroscopy. By splitting the incoming light into its constituent colors, a spectrum is revealed, a unique barcode of the elements within the galaxy. Scientists know the precise wavelength far these spectral lines have shifted. They can calculate the journey's true scale. For Jades, the evidence is unambiguous. Hydrogen emission lines, which should blaze in the ultraviolet, are found deep within the infrared. The shift is so extreme, there is no room for doubt. This galaxy is genuinely ancient. The light we see today began its voyage just 290 million years after the Big Bang. We are not merely looking at a distant object. We are receiving a message from the universe's infancy. It is a relic from a time when the first stars were igniting the darkness, and the seeds of the magnificent structures we see today were just beginning to be sown. The cosmic story, it seems, began not with a slow awakening, but with a thunderous roar. For more than 13 billion years, it has journeyed through a universe in constant, silent flight. A single photon, an ancient messenger from a dawn we have only ever imagined. The very fabric of space through which this light travels is not static. It is stretching, creating a profound paradox of distance. When astronomers speak of a galaxy 13.5 billion light-years away, they describe only the time the light has spent in transit. But in that immense span, the universe itself has expanded. If one could halt this cosmic inflation for a single moment, the true gulf between us and that galaxy would be revealed to be far greater, much greater. This is the co-moving distance, a measure of a universe that has grown around the light's relentless journey. To truly grasp the cosmos, astronomers turn not to distance, but to a more fundamental truth etched into the light itself, its redshift. It is a pure measure of expansion. It tells us, with absolute clarity, how much the universe has stretched since that light began its odyssey. A redshift of 14 is not merely a number, it is a revelation. It means the universe, and every photon within it, has been stretched by a factor of 15. This stretching is a thief. It robs the light of more than its color. It saps its energy, leaving each photon a weakened echo of its former self. And as the path itself expands, these photons arrive less frequently, their steady stream thinning to a trickle across the eons. The combined effect is a profound dimming, rendering the universe's earliest creations almost invisible. To capture these ghostly messengers, humanity has built an eye of unparalleled power. The James Webb Space Telescope compensates for this cosmic fading with an enormous mirror, a golden honeycomb that gathers every possible photon. Its detectors, chilled to within a few degrees of absolute zero, reduce the clamor of thermal noise, allowing them to perceive signals of almost unimaginable faintness. Even with such an instrument, the price of a glimpse into the past is time. The Jade's Deep Field, a landmark observation, required more than 70 hours of the telescope's focus. In a facility where every hour is a precious commodity, such an investment is monumental. Astronomers must prove that the scientific return justifies the cost. And discovering the most distant galaxy known to humankind certainly qualifies. The record is a frontier, constantly being pushed back. Before this new eye opened, the farthest known galaxy registered a redshift of 13.2. Now, the record has been shattered, pushed to 14.32, and beyond it, we know others are waiting. Webb has the power to detect galaxies with redshifts as high as 20, objects that formed in the first 200 million years after the Big Bang. But finding them is an epic challenge. They are rare. They are excruciatingly faint. It demands that we stare into vast patches of empty sky for days, patiently accumulating their whisper-thin light. It requires months, even years, of painstaking analysis, sifting through cosmic noise for a candidate, and then confirming its impossible distance with the unwavering science of spectroscopy. Each new record is the culmination of a colossal effort, but it is an effort that peels back the layers of creation, revealing fundamental truths about the moment of cosmic dawn. It is the search not just for the first galaxies, but for the first light to ever break the darkness. In the deepest recesses of time, the first galaxies were not hiding. They were not faint embers in the dark, but brilliant, roaring furnaces of creation, surprisingly mature. They blazed into existence within a cosmos that was expanding in a way that continues to defy our most fundamental understanding. At the heart of this cosmic mystery is a single number, a measure of the universe's outward rush, the Hubble constant. It is the fundamental yardstick of cosmology, telling us how fast the fabric of space itself is stretching. The current consensus places this value near 70 kilometers per second per megaparsec. The scale is almost unimaginable. A megaparsec is a gulf of roughly 3.3 million light-years. This means, for every 3.3 million light-years a galaxy is distant from us, it appears to recede an additional 70 kilometers per second. A galaxy 6.6 million light-years away flees at 140 kilometers per second. The pattern holds, a relentless expansion stretching across the eons. But to determine this cosmic speed limit, astronomers look to two vastly different epochs. The first method is a form of cosmic archaeology. Scientists gaze upon the most ancient light in existence, the cosmic microwave background. This is the faint, residual afterglow of the Big Bang itself, an echo of creation. Within its subtle temperature fluctuations lies a blueprint of the infant universe, from which cosmologists can calculate how fast that universe should be expanding today. Their prediction is precise, 67.4 kilometers per second per megaparsec. The second method looks not to the past, but to our own cosmic neighborhood. It relies on the violent deaths of stars, supernovae of a specific type that explode with a known preds their distance. By measuring these distances against the speed at which their host galaxies are receding, astronomers can measure the expansion rate directly. This method yields a different answer, a faster one, approximately 73 kilometers per second per megaparsec. 67.4 versus 73. The gap seems small, yet in the precise world of cosmology, it is a chasm. For decades, this discrepancy, the Hubble tension, has persisted, a stubborn crack in the foundations of our cosmic model. The James Webb Space Telescope, with its unparalleled vision, was meant to be the final arbiter. Many believed it would uncover a subtle error in one of the measurements, finally resolving the conflict. Instead, after compiling the most extensive dataset ever gathered on nearby supernovae, Webb delivered a stunning verdict. The measurements were correct. The local universe is indeed expanding at 73 kilometers per second per megaparsec. The tension is not an error, it is real. We are now faced with a profound choice of possibilities. One is that our entire understanding of the early universe is incomplete. The model used to interpret that ancient light from the Big Bang might be wrong. Perhaps dark energy, the mysterious force driving the acceleration, is not constant. Perhaps an unknown particle or force shaped the dawn of time in ways we have yet to imagine. The other possibility is even more unsettling. It suggests that we may live in a strange and unusual part of the cosmos, a Hubble bubble that is expanding faster than the universal average. The universe, it seems, is not giving up its secrets easily. The more precisely we measure it, the deeper the mystery becomes, reminding us that what we know is but a sliver of the shore, bordering a vast, dark ocean of the unknown. It is a possibility as unsettling as it is profound, that our entire galactic neighborhood resides within a vast, cosmic underdensity, a region where the fabric of space-time stretches at a different rate than the universal average. Yet all measurements of our local environment suggest otherwise, that we are in no special place at all. A third path presents itself, that the universe itself has not been constant, that its fundamental behavior has changed over the vastness of time. One of our cosmic views looks back to the dawn of light, a mere 380,000 years after the Big Bang, its story imprinted on the ancient glow of the microwave background. The other looks to the grand, explosive dance of supernovae across the last few billion years. The numbers they give us for the expansion of the cosmos do not align. The discrepancy suggests that somewhere in the unobserved chasm between the infant universe and its maturity, the rules of expansion may have fundamentally shifted. To reconcile this, some theorists are forced to consider the unthinkable. Perhaps gravity itself, on the grandest of scales, behaves in ways we do not comprehend. Perhaps the enigmatic force known as dark energy is not a constant, but a growing power, pushing the galaxies apart with ever-increasing ferocity. Each path leads to the same daunting destination, a modification of general relativity, the bedrock of modern cosmology laid down by Einstein himself. It is a step scientists are loath to take without irrefutable proof. Recently, a verdict came from the James Webb Space Telescope. For years, a simple explanation lingered, that the Hubble Space Telescope's measurements were skewed by a subtle, systemic bias. But Webb, with its entirely different instruments and techniques, stared into the void and returned the very same answer. The easy explanation has been eliminated. The tension is not an error, it is real. We are left with a stark and genuine mystery. Two of our most trusted methods for charting the cosmos, both refined over decades of rigorous work, are in direct conflict. One of them must be wrong, or something about the universe is profoundly more complex than our current models allow. In either case, a resolution will almost certainly demand new physics. And the mysteries extend beyond just the rate of expansion. Deeper in time, another, more elemental puzzle awaits. The very first stars. They were unlike anything that shines in the sky today, forged not from the recycled dust of their ancestors, but from the pristine, untouched gas of the Big Bang itself. A simple recipe of hydrogen, helium, and the faintest trace of lithium. There was no carbon, no oxygen, no iron. Nothing heavier than lithium existed. Astronomers call them population 3 stars. Not one has ever been directly observed. Every star we have ever studied contains at least some measure of heavy elements, and yet theory demands that they must have existed. Someone, or something, had to forge the first heavy elements. They had to be born in the hearts of that first, ghost generation. These primordial suns would have been titans. Without heavy elements to help cool the collapsing gas, only the most colossal accumulations of matter could overcome the intense pressure and ignite. Simulations suggest population 3 stars typically weighed 50 to 500 times more than our own home star. And as all massive stars do, they burned brilliantly and died young. A star 100 times heavier than our Sun exhausts its nuclear fuel in just a few million years, a fleeting, violent moment on the cosmic timescale. Their deaths seeded the void, enriching the universe generation of stars that had to exist, yet remain beyond our sight, a humbling reminder that the universe's most profound secrets may still lie hidden in its deepest past. In the grand cosmic theater, death is merely an overture to creation. A star, having lived its life, collapses and then erupts in a final, glorious supernova, scattering its chemically enriched heart across the interstellar medium. From this stellar dust, the next generation of stars is born, now containing the heavy elements forged in the crucibles of their ancestors. But before all this, there was a first generation, the pioneers. Astronomers call them population 3. Forged from nothing but the pure hydrogen and helium of the infant cosmos, these primordial giants should have vanished billions of years ago, their lives too brilliant and too brief to survive to the present day. Yet we might still see their ghosts. If we look far enough across space, we are also looking back through Tim, from when the universe was less than 500 million years old, an era early enough that some population 3 stars might still be shining. Finding them is a search for a whisper across an ocean of silence. A single, massive star is far too faint to be seen across billions of light-years of expanding space. So, astronomers hunt for a collective signature, the spectral fingerprint left by a multitude of these first suns burning together. The light from a star of pure hydrogen and helium is fundamentally different from one enriched with metals. Certain emission lines in their spectrum should blaze with intensity, while others remain weak or absent entirely. In a distant galaxy cataloged as GNZ11, we have found a tantalizing clue. This object is seen as it was just 430 million years after the Big Bang. Spectra gathered from its outer regions reveal a powerful hydrogen emission, with peculiar, unexpected ratios between its different spectral lines. The pattern is a near-perfect match for what theorists predict for a region where population 3 stars are being born. The evidence is not yet definitive. Other, more exotic cosmic processes could mimic these features, but the possibility alone electrifies the world of astronomy. If confirmed, this would be the first direct detection of the stars that brought light to the cosmos. These were the objects that seeded the universe with the first heavy elements, the raw material that would one day build worlds and eventually make life itself possible. Their influence was even more profound. They were the agents that ended the cosmic dark ages. In the aftermath of the Big Bang, the universe cooled, and primordial particles combined to form a vast, transparent fog of neutral hydrogen gas. Light could travel, but there were no stars to produce it. The universe was dark. When the first population 3 stars ignited, their ferocious ultraviolet radiation blasted through this fog, ionizing the hydrogen around them. They carved out immense bubbles of transparent, electrified plasma. As more and more stars came into being, these bubbles grew, overlapped, and merged, until the entire universe was once again ionized. This epoch of reionization was one of the last great transformations of the cosmos, and these first stars were its engine. Packed into early galaxies, they were reionization powerhouses, clearing the cosmic mist and allowing light to travel freely across the heavens. Today, the Webb Telescope hunts for them systematically, imaging and dissecting the light of hundreds of early galaxies. Each observation is a page turned in the universe's oldest story. We are searching for the first dawn, for the moment our cosmos truly began to shine, seeking the origin of the elements that constitute our worlds, our bodies, and our minds. In the light from the most distant heavens, a story is written. Each spectrum might contain the telltale signs of population, the chemical fingerprints of the very first stars. Even if only a small fraction of early galaxies still host these primordial suns, our deepest cosmic surveys were designed to find them. The discovery would connect us directly to the first chapter of cosmic history. We would see the ancestors of all stars, the original engines that transformed the universe from darkness into an era of light. But while the hunt was on for these cosmic progenitors, astronomers stumbled upon objects they cannot explain at all. They appear as tiny, crimson points in our deepest images of space. Compact, luminous, red. A deliberately vague name has been given to these enigmas that defy classification: little red dots. They exist in a distant past, at a cosmic redshift between 5 and 8, a time when the cosmos was merely 1 to 2 billion years old. Their crimson color is not the gentle light of stars, but the violent glow of hot gas surrounding a central black hole. As matter spirals inward, friction heats it to millions of degrees, forging an accretion disk that burns across the electromagnetic spectrum. A heavy shroud of dust obscures the shorter wavelengths, allowing only the red light to escape across the void. These objects are not rare. Large surveys have revealed dozens of them. They make up several percent of the entire galaxy population at these early epochs, a startling abundance that no one predicted. What makes them so profoundly confusing is their spectrum. When astronomers split their ancient light into its constituent wavelengths, the pattern reveals a deep contradiction. It shows the broad emission lines characteristic of a ravenous black hole, the signature of gas moving at thousands of kilometers per second. Yet it also shows the narrower features associated with star formation, the sign of gas moving much more slowly in stellar nurseries. Normally, these two signatures come from entirely different types of objects. Active galactic nuclei, powered by supermassive black holes, show the broad lines. Star-forming galaxies show the narrow ones. The little red dots, impossibly, show both simultaneously. Are they galaxies with unusually active black holes? Or black holes experiencing an unprecedented frenzy of star formation around them? Or are they something else entirely? The mystery deepens with their size. These objects appear as single points of light, their immense energy radiating from a region smaller than 1,000 light-years across. For comparison, our own Milky Way spans 100,000 light-years. These enigmatic dots pack tremendous power into a volume 100 times smaller than a typical galaxy. Some researchers argue they are simply a known phenomenon in heavy disguise. Quasars, the most luminous objects in the universe, obscured by dust. But whether they are a new class of cosmic entity or an extreme form of one we already know, they force us to confront the unknown. In our search for the beginning, we found not the answers we expected, but a set of questions far more profound. A stark reminder that the universe's capacity to surprise is as boundless as the darkness between its stars. In the deepest fields of cosmic time, where the light of the first galaxies has traveled for billions of years to reach us, a new mystery has emerged. They appear as tiny, crimson points against the primordial blackness. Enigmatic objects astronomers call little red dots. At their heart, a ravenous engine, a supermassive black hole, furiously consuming the matter of its infant universe. One theory suggests a simple disguise. If a quasar, one of the brightest objects known, is shrouded in a sufficient veil of dust, its brilliant visible and ultraviolet light is absorbed, only to be re-radiated as a faint, infrared glow. This cosmic shroud would make the beacon appear both red and deceptively compact. But another, more dramatic possibility points to a fleeting, cataclysmic adolescence in the life of a galaxy. Perhaps we are witnessing the very moment a galaxy forges its first supermassive black hole. The central engine has just ignited, its appetite for gas insatiable, creating the signature of an active nucleus. All the while, the surrounding host galaxy continues its own furious burst of star formation. In this view, the little red dot is a transitional phase, a cosmic becoming. Eventually, the black hole's power will grow so immense that its own energy will quench the star birth, and the object will mature into a typical quasar. A third hypothesis looks not to the object itself, but to its cosmic address. These little red dots are not scattered randomly. They cluster together, found at precise intersections within the vast, filamentary structure of the cosmic web. Perhaps their very existence requires the special conditions found only in these dense crucibles of the universe, where collisions between gas clouds or the gravitational dance of multiple small galaxies could trigger both the birth of stars and the rapid growth of a black hole all at once. To test these ideas, humanity has turned its most powerful eye to the dawn of time. Through the lens of the Webb Telescope, astronomers dissect the ancient light, measuring the mass of the black holes, the rate of star formation, the quantity of dust, and the chemical fingerprints left behind. One recent analysis examined 7 of these objects, all from the same cosmic epoch. The findings were startling. All 7 showed evidence of what are called overmassive black holes, with the central black hole accounting for an astonishing 10% of the galaxy's entire stellar mass. This profound consistency suggests we are not observing random cosmic oddballs, but a genuine, undiscovered population sharing a common, violent origin. Their sheer number forces us to reconsider how black holes form, favoring models of rapid, direct collapse in the early universe. Peering deeper still, the Webb reveals another layer to the enigma. Around some of these brilliant red cores, it detects a ghostly halo, a faint, extended emission. It is the host galaxy itself, so utterly dwarfed by the glare of its own active nucleus that it almost vanishes. Understanding the bond between this phantom galaxy and its brilliant, ravenous core is to understand how these two cosmic titans, the galaxy and its black hole, grow together, locked in a co-evolutionary embrace from the beginning of time. These little red dots represent one of the greatest surprises to emerge from our new window on the cosmos. No one anticipated finding so many. Each observation adds a new piece to the puzzle, yet the complete picture remains elusive, a reminder that for all we have learned, the early universe still holds its deepest secrets in the dark. On the grandest of scales, the universe is not a uniform void. It is a tapestry, woven by gravity. Matter, drawn together over eons, has formed a vast, luminous network, the cosmic web. Galaxies are not scattered at random. They congregate along immense filaments of dark matter, creating chains of light that stretch for hundreds of millions of light years. Where these filaments intersect, they give rise to colossal clusters, cities of galaxies bound by an immense gravitational pull. And between them lie the great voids, staggering expanses of near emptiness. This majestic architecture emerged from the faintest of whispers in the infant universe. Just after the Big Bang, reality was almost perfectly smooth, but not quite. Microscopic fluctuations in density, regions infinitesimally denser than their surroundings, held the seeds of everything to come. Over billions of years, gravity amplified these minute variations, pulling in more and more matter, sculpting the smooth beginnings into the intricate, clumpy cosmos we inhabit today. Now, a new eye on the cosmos allows us to trace this web back to its genesis. By mapping the positions of the most distant galaxies, astronomers can reconstruct the cosmic web as it was when the universe was less than 2 billion years old. The map reveals a staggering truth. The web was already there, a younger, more delicate version of its modern self. The filaments were less defined, the clusters only just beginning to coalesce. In one recent survey, a single patch of sky was scrutinized with unprecedented detail. Thousands of galaxies were identified, each a faint pinprick from a forgotten age. By measuring their redshift, the stretching of their light by the expansion of the universe, astronomers could place each one at its correct position in three-dimensional space, building a map that spans cosmic epochs. The evidence is clear. The cosmic web has been the fundamental architecture of the universe for most of its history. Even at a redshift of 8, when the universe was less than 1 billion years old, galaxies were not adrift. They were already clustering along filaments, the basic framework firmly established. What has changed is the scale, the filaments thickening, the nodes growing into the massive clusters we see today. Understanding this evolution is a crucial test of our cosmological models. The rate at which this structure grows is dictated by the unseen forces that dominate our universe: dark matter and dark energy. Too little dark matter, and the web forms too slowly. Too much, and it forms too quickly. The observed growth provides a vital constraint, a cosmic measuring stick. The skeleton of this entire structure is made of something we cannot see: dark matter, comprising some 85% of all matter, emits no light, reflects no light, and absorbs no light. Its presence is known to us only through its gravitational embrace. It is the invisible scaffolding upon which the visible universe is built. Galaxies form only in the densest pockets of this dark matter halo, tracing its ghostly contours across the heavens. And so, by mapping the light, we map the darkness. The galaxies are not the structure itself, but a biased, luminous echo of the true, underlying reality. They are the lamps, hung upon an invisible framework, that allow us to perceive the shape of everything. In the deepest chasms of space-time, they are born. Galaxies do not arise from happenstance, but are anchored to the unseen. They form preferentially within the most massive, most ancient concentrations of dark matter. To witness this is to witness the ghost in the machine of the cosmos. By charting the way galaxies cluster together, astronomers trace the contours of this invisible architecture, the dark matter skeleton that shaped all creation. To test their understanding, they build universes from light and logic. These simulations begin with the faint echo of the Big Bang, with initial conditions matching the infancy of the universe. Then, the clock is set forward. Billions of years of cosmic evolution unfold in a matter of hours. The results of these digital creations can be laid directly over the maps of the real, observed sky. Where simulation and observation align, our models of the universe are confirmed. But where they diverge, a deeper truth is hinted at. The signature of missing physics, of forces and processes we have yet to name. On the grandest of scales, our understanding holds. The sweeping filaments and vast, empty voids of the cosmic web appear in our simulations just as they do in our telescopes. But zoom in, and the beautiful consensus begins to fracture. On smaller scales, discrepancies emerge. Our models predict a chorus of small galaxies in some regions, where our telescopes find only silence, and a scarcity in others, where we find abundance. The implication is unsettling. The birth of a galaxy is an event far more complex, more nuanced, than our current theories can fully describe. This cosmic web is not merely a passive stage. It is an active participant in the lives of galaxies. Those born into the dense, crowded superhighways of the filaments evolve in a crucible of violence and creation. Here, interactions are frequent, and mergers are inevitable. These titanic collisions trigger furious bursts of star formation, while funneling rivers of gas into the waiting maws of central supermassive black holes. In contrast, galaxies adrift in the great voids lead a quiet, isolated existence. Their evolution is a slow, stately dance, undisturbed by the gravitational turmoil of their city-dwelling cousins. And within this geography, astronomers find strange new populations. Compact, crimson galaxies, once thought to be cosmic relics, do not appear everywhere. They are found clustered in specific locales, in the moderately dense regions along the great filaments. This profound environmental dependence is a clue, a signpost pointing to the unique conditions that forge them. Perhaps here, in the perfect balance of an ample gas supply and the constant jostle of interactions, the conditions are met for the explosive growth of a black hole, an engine that can transform a galaxy in an instant. By mapping the web at different epochs in cosmic history, we can watch the universe breathe. We see streams of primordial gas, the lifeblood of creation, flowing along the filaments toward the great clusters at their intersections. This gas feeds the galaxies it passes, fueling their stellar nurseries. But upon reaching the cluster, its journey ends in fire. It is superheated by shocks and turbulence, its star-forming potential extinguished forever. Here, the universe reveals its ultimate secret, an unbroken chain of influence connecting the smallest and largest of scales. The fate of a single star-forming cloud inside an individual galaxy is written by its address within the cosmic web, and the evolution of that web, in turn, is governed by the fundamental cosmological parameters that dictate the destiny of the universe as a whole. To study this structure is to probe the very foundations of physics, and yet, for all we have learned, a deep strangeness persists. In our own corner of the universe, galaxies exhibit a typical density, a predictable ratio of stellar mass to the volume it occupies. It is a consistency that is both comforting and confounding. Is this order a fundamental law of cosmic habitats, or merely a local quirk in a universe that remains, in its deepest heart, profoundly mysterious? In the deepest echoes of space-time, where the universe was still in its infancy, the familiar architecture of the cosmos seems to break down. This defies it completely. Measurements from the edge of observable reality reveal a startling truth. These high redshift primordial galaxies are staggeringly dense. Some are 1,000 times more compact than the galaxies that populate our modern cosmic neighborhood. They possess the same mass of stars, but crushed into a volume 1,000 times smaller. Within these galactic cores, stars wheel in tight, crowded orbits, where near collisions and gravitational disruptions would have been a common, violent reality. This discovery presents a profound paradox. If galaxies begin their existence as small, intensely dense objects, only to evolve into the vast, diffuse structures we see today, then some cosmic force must be puffing them up over billions of years. They must mass. This was the precise opposite of what our most sophisticated theories had predicted. Our simulations had consistently shown galaxies growing by accumulating matter, not by simply expanding into the void. One explanation lies in the universe's most majestic and violent events, galactic mergers. When two galaxies collide, their constituent stars, separated by immense voids, do not crash into one another. They pass through across the emptiness, and in this chaotic dance, the stars are fundamentally redistributed. The newly merged galaxy emerges from the encounter transformed, larger, more scattered, and significantly less dense than either of its parents. A history of repeated mergers, playing out over the eons, could be the mechanism that gradually dilutes the density of the cosmos. Yet another force may be at work, one that is entirely unseen. Every galaxy is thought to be enthroned at the center of a colossal halo of dark matter, a scaffold that extends far beyond the visible light of its stars. As this invisible halo grows, accreting more dark matter from the cosmic web, its gravitational landscape shifts. This subtle alteration of the fundamental forces can cause stars to migrate outward, compelling the galaxy to expand and occupy a larger volume, even if not a single new star is born. And then, there is the violence from within. The life and death of stars and the feeding of supermassive black holes can reshape a galaxy on the grandest scale. Powerful, energetic winds, driven by legions of exploding supernovae, or the fury of an active galactic nucleus, can blast gas out of the galaxy's core. This exodus of mass weakens the gravitational grip at the center. In response, stars drift into larger, more stable orbits, causing the entire system to swell, its density forever lessened. For a time, some astronomers questioned if this incredible density was merely an illusion, a phantom of observation. Measuring the precise size of an object 13 billion light-years away is a monumental challenge. It appears as little more than a faint smudge of light, and determining where the galaxy ends and the blackness of space begins requires assumptions. But the James Webb Space Telescope, with its unprecedented power to resolve the ancient universe, has settled the debate. Its gaze confirmed the truth. The early galaxies are, indeed, unnervingly compact. The effect is real. The story of their expansion is therefore woven into the very history of star formation. If galaxies forged the vast majority of their stars in a brief, brilliant blaze of creation early in their lives, and then grew primarily through the slow, steady process of mergers, it would explain this cosmic transformation. They are not static islands of light, but living, evolving entities. Their journey from dense, fiery youth to sprawling, placid maturity is a testament to the ceaseless and often invisible forces that sculpt the universe itself. Within the cosmic dawn, a profound mystery unfolds. The earliest galaxies, observed at the edge of time, are not what we expected. They are compact, dense knots of matter, fundamentally different from the sprawling island universes we see today. How did they transform? One theory suggested they simply expanded outwards, maintaining their mass while increasing their size, their density slowly diminishing over eons. But the piercing gaze of the Webb telescope reveals a flaw in this simple narrative. Many of these nascent galaxies are alight with furious star formation, a pace of creation that contradicts such a gentle evolution. Another answer lies not in the stars, but in the substance from which they are born: gas. Galaxies in the universe's infancy held a far higher fraction of gas compared to the star-filled cities of today. And gas is compressible. A galaxy rich in this raw material can be squeezed into a smaller volume, achieving immense density. But as the galaxy ages, a great conversion takes place. Gas collapses, ignites, and is transmuted into stars. And stars, once forged, do not compress further. This cosmic alchemy naturally drives the galaxy to expand, its overall density destined to decrease over billions of years. This observed evolution is more than a footnote in the story of a single galaxy. It is a test for our understanding of the cosmos itself. If the universe expands according to our accepted models, then the galaxies within it must evolve in a predictable way. Any disagreement between observation and prediction hints that either our model of the universe is wrong, or that the epic of galaxy evolution involves powerful processes we have yet to comprehend. Alternative visions of the cosmos, controversial and outside the mainstream, predict that distant galaxies should appear much the same size as those nearby. In these models, the stretching of light, the redshift, comes not from the expansion of space, but from motion through it. Webb's precise measurements of galactic density provide the hard data against which any model, orthodox or otherwise, must be judged. Whatever the final explanation, one truth is now self-evident. The galaxies of the early universe are not merely smaller versions of our own. They are alien in their structure, their dynamics governed by a different set of rules. Consider a single point of light, a galaxy designated Jades. It sits more than 13 billion light-years away. For nearly the entire age of the universe, its light has journeyed across the expanding fabric of space-time. By the time each photon completes its odyssey and strikes Webb's mirror, it has been stretched, redshifted, its energy bled away. The torrent of light has been diluted to a trickle by cosmic distances. It should be impossibly dim. And yet, it is bright, astonishingly bright. So bright that Webb could have detected it even if it were 10 times fainter. This stunning observation raises an immediate question. If this one brilliant galaxy is so easy to find, where are all the others that must exist at these same impossible distances? The answer is as simple as it is revolutionary. They are everywhere. Webb is finding them in droves, a multitude of brilliant galaxies at high redshift, far more than our models ever predicted. These beacons of light dominate the early universe in a way cosmologists never anticipated. The brightness of a galaxy is a direct measure of its star formation rate, and the message from these ancient photons is clear. The universe at cosmic dawn was not a dim and quiet nursery. It was a crucible, ablaze with the fire of creation, forging stars and shaping the cosmos we know today. Its violent and luminous youth far grander than we ever had the imagination to believe. In the deepest chasms of cosmic time, some galaxies blaze with an impossible light. This brilliance is not the gentle glow of age, but the fierce, incandescent signature of creation itself, powered by the ultraviolet fire of young, massive stars. By measuring this ancient light, correcting for its immense journey across an expanding universe, astronomers can read the story of a galaxy's birth and estimate the furious pace of stellar creation within. One such beacon, seen as it was in the universe's infancy, forges new stars at a prodigious rate. Estimates suggest the birth of dozens of suns worth of mass every single year. For perspective, our own Milky Way, in its quiet maturity, musters only 1 or 2. This primordial galaxy is tens of times more active, a furious engine of creation packed into a volume far smaller than our own. Its physical size presents another enigma. Spanning over 1,600 light-years, it is vastly larger than our models of the early cosmos predicted. Simulations suggested these first stellar cities would be tiny hamlets, perhaps only a few hundred light-years across. This ancient structure is a metropolis, born far ahead of its time. The mystery of its brightness is, in truth, a question of efficiency. What fueled this frantic pace of star formation in the universe's dawn? One factor was fuel, in unimaginable abundance. The first galaxies were saturated with pristine gas, mostly hydrogen and helium, which had not yet been locked away into stars. This raw material flowed in along the filaments of the cosmic web, a steady, inexhaustible torrent, providing the substance for creation. A second factor lies in what was missing. In the modern cosmos, heavy elements forged in stars condense into dust. This dust helps cool gas, allowing new stars to form, but it also acts as a shroud, absorbing light and dimming a galaxy's appearance. These early galaxies were clean, transparent. With little dust to obscure the view, their starlight, unimpeded, streamed across the cosmos, making them appear far brighter than a modern counterpart of similar output. And then there is the question of regulation. In nearby galaxies, the violent deaths of stars and supernovae and the powerful winds from supermassive black holes act as a galactic thermostat. They heat and expel gas, preventing it from collapsing and thereby throttling star formation. But in the beginning, these feedback mechanisms were weak. Black holes were still growing, and the cosmos was not yet heavily enriched by supernova remnants. With the governors offline, the engine of star birth could run wild. But even these potent explanations fall short. When we feed this rich gas, this lack of dust, and this weak feedback into our most sophisticated simulations, they still fail to forge a galaxy as luminous as the one we now see. A profound gap persists between theory and observation. The light from this primordial galaxy, traveling for billions of years to reach our telescopes, illuminates not only the dawn of the cosmos, but the very limits of our own comprehension. Across the unfathomable darkness of cosmic dawn, a profound mystery is unfolding. The first galaxies, infant islands of light emerging from the primordial void, are shining with an intensity that defies our understanding. Our models of the early universe predicted a slow, gradual awakening. What we are witnessing is something far more brilliant, far more violent. One theory suggests we are catching these ancient structures in a fleeting, spectacular phase of their youth, a starburst. In the chaotic aftermath of a galactic merger, or when flooded by a sudden massive influx of pristine gas, star formation can ignite into a frenzy. For a few tens of millions of years, a mere flicker in cosmic time, these galaxies blaze with the light of countless newborn suns. If our gaze happens to fall upon them during this brief, incandescent period, they would appear impossibly luminous, outliers in the grand celestial story. But another, more fundamental possibility exists, one written into the very recipe for the stars themselves. Here, in our local cosmic neighborhood, the universe tends to build small. For every massive, brilliant star, countless smaller, dimmer ones are born. But what if the cosmic forge operated differently at the dawn of time? If the early universe favored the creation of giants, massive, blue-white stars that burn hot and die young, then the galaxies they inhabited would radiate with an astonishing ultraviolet ferocity. They would appear brighter, not because they were forming more stars, but because the stars they formed were titans. To distinguish between a fleeting phase and a fundamental truth requires a census of cosmic proportions. The James Webb Space Telescope is now undertaking that survey, staring deep into the past to build a statistical portrait of the universe's first light. By examining hundreds of these nascent galaxies, astronomers can determine if the bright objects are rare exceptions or the norm. The data, as it arrives, points to a stunning conclusion. They appear to be typical. The early universe was not just sporadically bright, it was genuinely, fundamentally more luminous than we ever imagined. This revelation sends ripples through our understanding of cosmic history, touching upon the epoch of reionization, the moment the universe's first light burned through the opaque fog of neutral hydrogen, rendering the cosmos transparent. These brighter galaxies would have been prodigious factories of ionizing photons. If there were more of them than expected, they would have produced a deluge of sterilizing radiation, potentially reionizing the universe faster and earlier than our previous models allowed. Webb's continued observations of this era will put that very idea to the test. Yet, as this instrument gazes to the edge of time, it also turns its eye to our most immediate cosmic neighbors. Just over 4 light-years from Earth, a mere stone's throw in galactic terms, lies the Alpha Centauri system. 3 stars, locked in a complex gravitational dance. 2 of them, Alpha Centauri A and B, are siblings to our own Sun. The third, Proxima Centauri, is a diminutive red dwarf. For decades, this system has been a beacon for our imagination, the most logical place to begin the search for other worlds. We know that Proxima Centauri hosts at least 2 planets, one of which orbits within the coveted habitable zone, where liquid water might grace a rocky surface. But searching for worlds around Centauri A and B are so brilliant, so close, that their overwhelming glare has blinded our instruments, washing out the impossibly faint signal of any orb BF, a searchlight. But Webb has changed the game. Using a custom-designed strategy with its mid-infrared instrument, astronomers dared to peer directly into the blinding heart of Alpha Centauri A, filtering through the stellar glare. And there, they found something. A faint, persistent source of infrared light, situated at roughly twice the distance Earth is from our Sun. The signal is consistent with a world far larger than our own, perhaps a gas giant, a silent sentinel orbiting the very next star. From the first furious light of creation to a potential world next door, the same lens is bringing 2 universes into focus, the universe of our origins and the universe of our future. We look out to the farthest shores of space and time to understand how everything came to be, and we look to our nearest neighbors for a sign that we are not alone. In this dual quest, we find not just the story of the cosmos, but the evolving story of ourselves. It is a signal born of deep caution, a whisper from the void that must first be separated from the noise. It could be nothing at all, a ghost in the machine, an artifact of the instrument, or a faint echo from some distant background object masquerading as a world. But if it is real, it represents the closest planetary neighbor humanity has ever known outside our own solar system, save for the small, silent worlds orbiting Proxima Centauri. To find a planet here, at Alpha Centauri, would be a discovery that redefines our cosmic backyard. The star system is so near that for the first time, a journey to a Nolam for a future generation. Detailed studies of such a world would offer profound insights into the birth of planets and the conditions for habitability. Its very existence would be a crucial piece in the grand puzzle of planetary architecture. The detection itself is a testament to ingenuity. The James Webb Space Telescope was conceived to peer back to the dawn of time, to capture the faint, ancient light of the universe's first galaxies. It was never intended for the blinding glare of a star on our doorstep. Yet, through clever and audacious strategies, astronomers have turned this magnificent instrument inward, proving its versatility. Its scientific reach now extends from the edge of creation to the sun next door, ensuring that the most startling discoveries may arise from the most unexpected of places. Alpha Centauri. If a gas giant orbits there, it was likely born from the same epic process that built Jupiter and Saturn, a solid core, forged from the patient collision of countless planetesimals, grows over millions of years, until its gravity becomes an inescapable force, pulling in the vast, swirling gases of the primordial disk. This potential world orbits within the system's habitable zone, that temperate region where liquid water could exist. As a gas giant, it would possess no solid ground, but giants are often parents to families of moons. If this world exists, and if it holds large, rocky moons in its sway, then those moons could be sanctuaries for life. It is a scenario mirrored in our own solar system, where the ice-shelled moons of Europa and Enceladus hide vast, subsurface oceans. To see such moons would demand technology beyond even Webb. They would be impossibly faint sparks, lost in the overwhelming light of their parent star and the reflected glare of their planet. That vision belongs to future missions, to great observatories that will deploy star shades or advanced coronagraphs, unfurling structures designed to cast a perfect, artificial eclipse across interstellar space, silencing the star to reveal the secrets in its orbit. The Alpha Centauri system serves as a crucial test case, a cosmic mirror held up to our own. By studying the pecs of our solar system are typical, and which are truly unique, it is the context that helps answer the ultimate, taking anomaly? Should future observations solidify this phantom into a fact, the planet will become a beacon for study. Astronomers will chart its precise orbit, weigh its mass, and decode the chemistry of its atmosphere. But for now, it remains a fragile possibility, a question mark hanging in the dark. And perhaps that is its greatest value. It is a reminder that discovery is not a single moment of revelation, but a long, difficult, and uncertain pursuit. A journey that forces us to push our knowledge and our tools to the absolute limit, all for a glimpse of what lies just beyond our reach. The search extends beyond the glow of distant galaxies, turning inward to the architecture of our own cosmic neighborhood. Here, the great telescope scours the darkness for unseen worlds, for the faint signature of planets yet to be named, and for the ghostly halos of debris disks, the primordial dust left over from creation. Its gaze is revealing the universe at every conceivable scale, from the first structures born in the cosmic dawn to the planetary systems taking shape next door. And in the process, it has uncovered a profound secret, hidden not in the heart of a star or the swirl of a galaxy, but in the vast, quiet emptiness in between. This interstellar space, long imagined as a near-perfect void, is a realm of ghosts. It is filled with gas and dust, a tenuous mist spread across light years, its density so low it defies comprehension. In the coldest, darkest regions, this material gathers, collapsing into great molecular clouds, the stellar nurseries where new suns ignite. But between these nascent cradles, a finer, more ethereal medium pervades the galaxy. Through the lens of a cosmic phenomenon known as a light echo, the telescope peered into the aftermath of a stellar explosion in the constellation Cassiopeia. What it saw was not a uniform, featureless expanse. Instead, the interstellar material was revealed to possess a breathtakingly intricate internal structure. Scientists measured features as small as 400 astronomical units across, vast on a human scale, yet impossibly delicate on a galactic one. They appeared as tightly packed sheets of matter, stacked. This single observation shattered a long-held view. Where astronomers once saw smooth, placid clouds, stirred only by a gentle turbulence, a new, far more complex reality emerged. The infrared vision of the telescope, combined with the fleeting illumination of the light echo, brought a hidden architecture into focus for the very first time. These sheets are not an anomaly. They are real, and they are ubiquitous. The sculptor of this realm is likely the unseen hand of magnetism. Across the interstellar medium, atoms are ionized, stripped of their electrons, and thus beholden to magnetic forces. As this charged gas moves, it drags the magnetic field lines with it, and over eons, this cosmic dance organizes the material into elongated structures, a tapestry woven by invisible forces. But there is another artist at work: turbulence. The interstellar medium is a place of chaos, constantly churned by the death cries of supernovae, the relentless pressure of stellar winds, and the subtle pull of gravity. This energy cascades through the void, creating a storm of chaotic motion that forges structure at every scale, from the expanse of entire clouds down to the smallest eddy. These newly discovered sheets may be the very channels that guide the flow of creation. Stars are born when gas collapses under its own weight. If these structures direct the movement of that gas, they could fundamentally influence where and when new stars ignite. The intersections of these sheets, regions of compression and density, may be the galaxy's most fertile grounds for birth. We are, for the first time, mapping the invisible highways of the galaxy. The observations provide a stark benchmark, a physical truth against which all our theoretical models of turbulence and magnetized plasma must now be tested. In the quiet spaces between the stars, we find not an absence, but an intricate design. We have discovered that even the void is governed by order, a testament to the fundamental forces that shape not only the grandest galaxies, but the very possibility of worlds yet to come. When our models of the universe align with observation, it is more than a simple validation. It is a confirmation that we have grasped some essential truth of the physics that governs all things. With instruments of unprecedented power, we now probe the fine, intricate structures of the cosmos. This is the power of infrared astronomy, where visible light falters, scattered and absorbed by vast clouds of interstellar dust. Entire regions of space are rendered opaque, their secrets locked away. But infrared light passes through this cosmic veil, penetrating the dust to reveal what lies within. By observing the universe at these specific wavelengths, the James Webb Space Telescope perceives a reality forever hidden from conventional view. A new technique, known as the light echo, promises to map this hidden realm. Each supernova, each brilliant, transient event, acts as a flashbulb in the dark, illuminating a different volume of interstellar space. By observing a series of these echoes, astronomers can begin to assemble a true, three-dimensional chart of the interstellar medium, a comprehensive picture of how matter organizes itself in the gulfs between the stars. And knowing this structure is paramount. It is the key to understanding the very efficiency of star formation. If interstellar gas is organized into dense, sweeping sheets, the process of gravitational collapse may proceed in a manner entirely different than in a smooth, uniform cloud. These sheets might first fragment into long, winding filaments, which in turn break apart into the individual, dense cores from which new stars are born. This hierarchy of structures ultimately determines not only how many stars will form, but the masses they will achieve. Just as it unveils the hidden architecture of nearby space, Webb is pioneering new methods to grasp the sheer scale of the cosmos. Measuring cosmic distance remains one of the greatest challenges in all of science. For the stars in our own celestial neighborhood, the method of parallax provides a reliable answer. By observing a star from opposite sides of Earth's orbit, it appears to shift its position against the distant background. The magnitude of that shift reveals its distance. But for the remote galaxies, this method fails. The apparent shifts become infinitesimally small, impossible to measure. To bridge these immense voids, astronomers rely on beacons known as standard candles, celestial objects whose intrinsic brightness is known. By measuring how bright they appear from Earth, we can calculate how far away they must be. The pulsating rhythm of Cepheid variable stars serves this purpose for nearby galaxies. A direct relationship exists between the period of their pulse and their luminosity. Measure the rhythm, and you know the true brightness. For even greater distances, we turn to the cataclysmic death of stars. Type 1a supernovae, born when a white dwarf star siphons matter from a companion until it reaches a critical mass, detonate with a remarkably consistent and predictable brilliance, making them one of the most reliable distance indicators we have. Now, Webb has validated another, more subtle technique, using the final life stages of ancient stars. Low-mass stars, late in their lives, swell into red giants. As they evolve, their brightness steadily increases until they reach a final, definitive peak, a maximum luminosity beyond which they cannot go. This tip of the red giant branch provides a new, crucial rung on the cosmic distance ladder. With every new method, every new way of seeing, the universe is measured and mapped with greater precision. The hidden structures and the vast distances are no longer matters of pure conjecture, but of observation and evidence, revealing a cosmos more intricate and more immense than we ever dared to imagine. At the very apex of its stellar life, a red giant star achieves a final, predictable peak of brilliance. This luminous ceiling, known as the tip of the red giant branch, is remarkably consistent across the cosmos. By seeking out these stellar beacons in a distant galaxy and identifying the very brightest among them, astronomers can triangulate their position in the vastness of space, calculating the galaxy's distance from us with newfound precision. For this delicate task, the James Webb Space Telescope is an unparalleled instrument. Its gaze, tuned to the infrared spectrum where red giants burn brightest, can resolve individual stars and galaxies tens of millions of light years away. Now, a newer method joins the cosmic survey, turning its attention to a different kind of celestial marker, the carbon star. These are evolved suns, their atmospheres uniquely enriched with the very element of life. In the near-infrared, these carbon stars exhibit a consistent color and brightness, serving as another, independent form of standard candle. Webb has begun applying this technique, measuring the distances to our galactic neighbors with this novel yardstick. The true power, however, lies not in a single method, but in the convergence of many. A recent landmark study brought three independent techniques to bear: the pulsating Cepheids, the tip of the red giant branch, and the nascent carbon star method, to measure the distances to 10 separate galaxies. The results provided a powerful cross-check. For each galaxy, all three methods agreed. They converged on a single value for the universe's expansion rate, 70 kilometers per second per megaparsec. This number falls directly into the gulf that has divided cosmology, a value lower than that derived from distant supernovae, yet higher than the one inferred from the faint afterglow of the Big Bang. The Hubble tension, that vexing discrepancy at the heart of modern physics, may be less severe than once feared, or perhaps it signals a reality far more complex. This agreement also serves as a profound validation. Some had questioned whether Webb's own instruments might harbor systematic errors, subtly skewing its distance estimates. But by demonstrating that three completely different techniques yield the same consistent answers, the study silences those doubts. The telescope is measuring the universe with unerring accuracy. Refining this single number, the Hubble constant, is a quest of fundamental importance. It is a parameter that dictates the universe's age, its ultimate scale, and its eventual fate. Every improvement in its precision narrows the field of possible cosmic models, sharpening our predictions for the grand evolutionary arc of everything that is. As astronomers gain experience with the new carbon star method, its calibration will be refined, its uncertainties reduced. Future observations with Webb will extend these measurements to ever more distant galaxies, honing the Hubble constant still further. A consistent picture, drawn from a symphony of wavelengths and techniques, will eventually emerge. Each new measurement, each confirmed distance, is another step out of the darkness, revealing not only the mechanics of the cosmos, but the very nature of our own inquiry into the grand, silent expanse that surrounds us. At the precipice of oblivion, where space and time unravel, gas spirals into the gravitational maw of a supermassive black hole. Here, in the final moments before crossing the event horizon, friction ignites a cosmic inferno, heating the material to millions of degrees. From this superheated maelstrom, a torrent of energy radiates across the entire electromagnetic spectrum. The sheer pressure of this light becomes a physical force, pushing back against the torrent of infalling gas, giving birth to titanic winds that scream away from the black hole at thousands of kilometers per second. These are not mere storms. They are cosmic hurricanes that sculpt the fate of entire galaxies. When the central giant feeds, these outflowing winds sweep in gas from stellar nurseries. Without this raw material, the birth of new stars grinds to a halt. The galaxy's great engine of creation is silenced. This monumental process, known as feedback, stands as one of the most crucial mechanisms governing the evolution of the cosmos. Through the golden eye of the Webb Telescope, we are witnessing this ancient drama unfold in the dawn of time. Distant galaxies, harboring black holes inexplicably massive for their size, show the telltale signs of these powerful outflows. The very light from these realms carries a spectral fingerprint, a signature of gas fleeing the galactic center at extreme velocities. The fastest of these outflows reach speeds of 3,000 kilometers per second, a velocity so immense the gas escapes the galaxy's gravitational pull entirely, cast out into the intergalactic void. Herein lies the solution to a cosmic riddle. Why these early galaxies, with such monstrous black holes, remain so small? The sequence of creation is inverted. The black hole ignites first, gorging on primordial gas and growing with astonishing speed. As it feeds, its energy output becomes a gale force, a galactic barrier that prevents the surrounding galaxy from forming a multitude of stars. The central engine, in its furious youth, stunts the growth of the very galaxy that birthed it. But this reign of fire cannot last forever. Eventually, the black hole exhausts its immediate fuel. Its accretion rate plummets, its energy output fades, and the great winds weaken. Only then can the remaining gas cool, collapse, and finally begin the patient work of building stars. The galaxy enters a new era of rapid formation, slowly, over hundreds of millions of years, building its stellar mass until the ratio between it and its central black hole approaches the equilibrium we see in the universe today. We are capturing these systems in their infancy, a fleeting moment when the black hole has won the race, and its galactic host has not yet had time to catch up. This expelled gas is not lost to the void. It flows into the vast, dark spaces between the galaxies, enriching the intergalactic medium with heavy elements, forged in the hearts of long-dead stars. This enriched material becomes the seed for future creation, destined to one day fall back into other galaxies, fueling new generations of stars. It is a vast, interconnected cycle, linking the destiny of a single object to the grand architecture of the entire cosmic web. We have learned that the universe is not built on quiet accumulation alone. It is shaped by a profound and violent balance, a cosmic conversation between creation and destruction, where the very engine of growth must first act as an agent of suppression. In the digital realms of cosmic simulation, a profound discrepancy emerged. Our models of the early universe were building galaxies that were too large, too quickly, a picture at odds with the cosmos we observed. The missing element was a force of staggering violence and precision, the feedback from supermassive black holes. The immense energy erupting from their cores acts as a cosmic regulator, a governor on the engine of star formation, sculpting galaxies across billions of years. Now, the Webb Telescope peers into this primordial era, testing these theories against ancient light. It captures galaxies frozen in time, some convulsed by active outflows, others in a state of quiet formation. By comparing these cosmic fossils, astronomers can decode the triggers for this feedback and measure its fleeting, powerful lifespan. Yet the influence of these first cosmic structures extended far beyond their own boundaries. As they carved out their domains, they were participants in an even grander transformation, the lifting of a universal veil. In the immediate aftermath of the Big Bang, the universe was an incandescent sea, a plasma of free-roaming protons and electrons, glowing with primordial light. But as expansion stretched the fabric of space-time, it cooled. Below a threshold of 3,000 degrees, electrons and protons bound together, forming atoms of neutral hydrogen. The universe, for the first time, became transparent. But in doing so, it fell into a profound darkness. This was the dawn of the cosmic dark ages. For millions of years, no stars shone. A cold, neutral hydrogen fog permeated everything, a shroud that would instantly absorb any high-energy light attempting to cross it. Then, out of the darkness, the first points of light ignited. The first stars, massive, brilliant, and short-lived, blazed into existence. Their ferocious ultraviolet radiation shattered the hydrogen atoms around them, splitting them back into protons and electrons. This newly ionized gas was transparent once more. Around each stellar furnace, a bubble of clarity began to grow, pushing back the cosmic fog. As countless more stars and galaxies ignited, their individual bubbles expanded, overlapped, and merged, until the entire intergalactic medium was cleared. This monumental phase change, one of the last great transformations of the universe, is known as the Epoch of Reionization. To witness this event is Webb's primary mandate. Its gaze is fixed on the most distant galaxies, seen as they were during this critical era, at redshifts between 6 and 10, a time when the universe was still a patchwork of shadow and light. By studying these pioneers, astronomers can calculate the sheer number of ionizing photons they unleashed, and map the pace at which the darkness receded. But a crucial question remains: how much of this liberating light ever escaped its home galaxy? Dust and gas within these nascent systems could trap the very radiation needed to clear the cosmic fog. This escape fraction is the key variable. To measure it is to understand the efficiency of reionization itself. Within the detailed spectra captured by Webb lie the chemical fingerprints, the subtle clues that reveal just how many photons won their freedom. In this cosmic ballet, we see the universe in a constant state of becoming. Forces of immense destruction, the outbursts of black holes, are the very sculptors of creation, and the first light, born to banish a universal darkness, had to first fight its way out of its own cradle. To decipher these ancient signals is to understand not just how galaxies are made, but how the universe itself learned to see. Within the ancient light of the first galaxies, specific spectral signatures betray a fundamental secret: whether the torrent of ultraviolet photons forged in their stellar nurseries was being contained, or if it was escaping to wage war on the cosmic darkness. Galaxies with a high fraction of this escaping light were the engines of change. By hunting for their unique chemical fingerprints, astronomers can now estimate just how many of these early systems contributed to the great transformation of the universe. Current observations suggest that the majority of them were remarkably efficient, releasing their ionizing radiation into the vast, empty spaces between worlds. This finding, combined with the surprisingly large number of bright, young galaxies uncovered by the Webb telescope, points to a revolutionary conclusion. The reionization of the universe may not have required stars. Instead, the colossal task appears to have been accomplished by the collective effort of ordinary star-forming galaxies. They alone did most of the work. Yet the timeline of this event remains shrouded in mystery. Most evidence suggests the process was complete by a time known as redshift 6, roughly 1 billion years after the Big Bang. But when it began and how long it took are still open questions. Did the universe reawaken in a sudden, violent burst over a few 100 million years? Or was it a slow, gradual sunrise that stretched for a billion? Observations are now constraining this history. By measuring the amount of neutral hydrogen gas at different cosmic epochs, astronomers can map the progress of reionization. Early results indicate a dramatic acceleration around redshift 8. Before that moment, the transformation was slow, a tentative advance. Afterward, the remaining fog of neutral gas was swept away with astonishing speed. Another puzzle lies in its topology. Did the bubbles of ionized plasma expand uniformly in all directions? Predict that these ionized regions would preferentially expand along the great filaments where galaxies cluster, leaving the immense cosmic voids to remain neutral for far longer. To test this requires mapping both the ionized regions and the distribution of galaxies at the same time. Through vast surveys, Webb is beginning to provide these maps, capturing the light and spectra of thousands of galaxies across wide swaths of the sky. Combined with measurements of the intergalactic medium, these data are revealing how reionization unfolded in 3 dimensions. The emerging picture is not of a simple, uniform event, but of a patchy and complex process that varied immensely from one region of the cosmos to the next. And one of the most powerful tools for this exploration comes from an unexpected source. Einstein's theory of general relativity predicts that mass warps the very fabric of space-time. Light, traveling through this disto of galaxies, sits between our telescopes and an even more distant galaxy. The cluster's immense gravity bends the background light. This bending can magnify the distant object, making it appear brighter and larger than it otherwise would. It is a phenomenon known as gravitational lensing, a cosmic telescope built by nature itself. Through these gravitational lenses, we are peering deeper into the dawn of time, using the fundamental laws of the universe to witness its own awakening. It is a lens not of glass, but of gravity itself, a natural telescope forged in the void, magnifying the deepest secrets of the cosmos, objects that would otherwise remain forever lost in the faint, distant dark. The James Webb Space Telescope systematically harnesses this cosmic phenomenon, known as gravitational lensing, to peer into the universe's dawn. Its gaze is fixed upon the titans of the cosmos, massive galaxy clusters. Through them, the telescope gains access to galaxies hidden behind, their ancient light amplified by factors of 10 or even 100. One such target was a cluster designated Abell S1063, a colossal gathering of galaxies some 4.5 billion light-years from Earth. Its immense gravitational field warps the very fabric of space-time, smearing the light of more distant galaxies into ghostly arcs and multiple phantom images. In a single exposure, Webb captured hundreds of these distorted background worlds. Some of these lensed galaxies shine with light from a time when the universe was less than 1 billion years old. Without the magnifying power of the cluster, they would be utterly undetectable. Even for Webb, the unaided view would reveal nothing but blackness. The gravitational lens makes the impossible possible. This cosmic magnification allows for more than mere detection. It permits an intimate study of individual galaxies. When a galaxy's light is stretched by a factor of 50, features once too small to resolve swim into focus. Astronomers can map the distribution of star formation, identify individual star clusters, and measure properties that would otherwise demand telescopes far larger than any ever built. In one lensed galaxy, Webb resolved 10 distinct star clusters. Each represents a stellar nursery, a region where stars ignited in unison from a collapsing cloud of gas. The clusters are of different ages, revealing a history of star formation that occurred not as a continuous flow, but in dramatic, successive bursts. This level of detail is a gift, bestowed only because gravity magnified the galaxy enough to unveil its internal life. The degree of magnification is a delicate dance of cosmic alignment. If a background galaxy is positioned directly behind the heart of the lensing cluster, the amplification can be extreme. Even slight misalignments produce less magnification, yet still provide a crucial boost. To understand what they are seeing, astronomers meticulously model the cluster's mass, calculating the precise magnification for every single object caught in its gravitational web. But the lens does not only reveal what is behind it, it also reveals itself. The precise pattern of distortion is a direct signature of how mass, both visible and invisible, is distributed within the cluster. By analyzing the shapes and positions of the lensed galaxies, astronomers can create a detailed map of the cluster's total mass, including the elusive scaffolding of dark matter. In the most profound instances, these cosmic mirages produce multiple images of the same background galaxy. Light, traveling from a single source, takes different paths around the immense gravitational obstacle, arriving at Earth at slightly different times, from slightly different directions. We see the same galaxy in 2, 3, or even more places in the sky at once, echoes of light, bent by the oldest force in the universe. Thus, the very force that binds the cosmos together also bends our perception of it, offering a warped yet profoundly clear window into the beginning of time. Across the void, gravity itself becomes a lens. By comparing these warped portraits of space-time, the very fabric of general relativity is put to the test, and the invisible architecture of dark matter within colossal galaxy clusters is mapped with breathtaking precision. The Webb Telescope has turned its gaze upon dozens of these cosmic lenses. With each observation, a new tapestry is revealed, woven with the light of hundreds of background galaxies, their images stretched and smeared into ghostly arcs. The cumulative result is a census of the cosmic dawn, a catalog of thousands of impossibly distant galaxies, many magnified into focus, ready for detailed study. This newfound sample is rewriting our understanding of how the first star cities were built in the universe's first billion years. But to simply see these ancient phantoms is not enough. The true power lies in combining this cosmic magnification with spectroscopy, decoding the light itself. Webb captures the spectra of these lensed galaxies, laying bare their chemical DNA, their rates of star birth, the very state of their primordial gas. This magnification makes it possible to interrogate galaxies that would otherwise be far too faint, their whispers lost in the cosmic silence. These measurements offer an unprecedented window into the properties of typical galaxies during the age of reionization, and some of what they reveal is entirely unexpected. In the distorted light of one massive galaxy cluster, a single, elongated arc appeared. Gravitational lensing had stretched its form and amplified its faint glow. Astronomers, struck by its appearance, nicknamed it the Firefly Sparkle. As they looked closer, they found something remarkable. Within this single sliver of light were 10 distinct, brilliant clusters of stars, each one clearly resolved by Webb's unparalleled vision. This was a galaxy that existed just 600 million years after the Big Bang, a time when the universe was less than 5% of its current age. Most galaxies observed from this epoch appear as solitary, compact smudges of light, but the Firefly Sparkle showed clear internal structure, 10 individual points of light. An analysis of each cluster revealed they were not uniform. They possessed different ages and masses. Some blazed with the fire of young, hot stars, only a few million years old. Others held slightly older stellar populations. Their masses ranged from a few thousand to several 100,000 times that of our Sun. Together, they amounted to a stellar mass of about 10 million suns. For a galaxy, this is astonishingly small. Our own Milky Way contains over 100 billion solar masses and stars. The Firefly Sparkle possesses less than 1/10,000th of that. And yet, this lightweight galaxy may be a mirror to our own distant past. Both its age and its mass align with predictions for what the Milky Way itself. The discovery is a powerful demonstration that many have crisped by piece from much smaller systems. The Firefly Sparkle is not a finished galaxy. It is a building block, a proto-galaxy caught in the very act of becoming, over billions of years, coalescing into the grand spirals we see today. Those 10 star clusters are more than just data. They are a snapshot of creation in action, a freeze frame from the earliest moments of cosmic history. In looking out at this fragile flicker of light, we find not a stranger, but an ancestor, a blueprint for the very galaxy we now call home. In the violent dawn of the cosmos, the first galaxies were not built in a steady, continuous creation. They were forged in fire and silence, in a great, rhythmic pulse. Across the void, vast clouds of primordial gas, drawn together by their own immense gravity, began to collapse. Each collapse ignited a cluster of new stars. The evidence is written in the starlight itself. The varied ages of these ancient clusters reveal a profound truth. Star formation did not happen all at once. Instead, it unfolded in distinct, explosive bursts, separated by millions of years of quiet. The process was a cosmic cycle, a galactic heartbeat. Gas, streaming into the young galaxy along the invisible filaments of the cosmic web, would accumulate. When a critical mass was reached, it triggered a firestorm of star birth. But the feedback from these brilliant, newborn suns, their fierce radiation and stellar winds, would heat the remaining gas, blowing it outward and temporarily halting the process. A pause until the relentless pull of gravity could gather new material, and the cycle would begin again. This episodic, convulsive mode of creation may have been the standard for all galaxies in their infancy. To witness this ancient drama, we look to a phantom, an object named Firefly Sparkle. It would have been utterly invisible, a faint smudge lost to time, were it not for a trick of space-time. A massive object in the foreground acts as a natural gravitational lens, magnifying its light by a factor of approximately 30. This cosmic telescope brought the galaxy into sharp relief, bright enough for the Webb Space Telescope to resolve its individual star clusters. The combination is a powerful microscope, allowing us to peer into the fine details of the early universe. What we see there, and in other lensed galaxies, is a pattern. Star formation was clumpy, concentrated in distinct, brilliant knots rather than spread smoothly through the galactic volume. This structure likely reflects the turbulent, unstable conditions of those primordial gas reservoirs, where instabilities caused the gas to fragment into dense clumps, each one a cradle for a new generation of stars. These very clumps may be the ancestors of the majestic structures that haunt the outskirts of our own galaxy today, the globular clusters. These are ancient spherical cities of stars, containing hundreds of thousands, even millions of suns, all packed into a volume just a few dozen light years across. Their immense age tells us they were born in this early, chaotic era. The star clusters of Firefly Sparkle possess similar masses, suggesting they are the precursors, the building blocks, that might one day evolve into the silent, glittering globes that orbit the Milky Way. By studying these distant proto-galaxies, we connect the remote past to our immediate present. In understanding how they assembled themselves, piece by brilliant piece, we our own cosmic history, written in photons that have traveled for billions of years to reach us. And yet, within this grand construction, an even more intimate story was unfolding. As these stars ignited from collapsing clouds of gas and dust, the raw materials for planets, and perhaps for life, were being forged. Each collapsing cloud flattened into a rotating disk. At its center, a star would blaze into existence, surrounded by a swirling platter of leftover material, all that would ever be available to form planets, moons, and comets. Peering into one such nascent stellar system, the Webb Telescope detected a chemical signature of profound significance. There, in the protoplanetary disk, was crystalline water ice, the most essential ingredient for life as we know it, already present in its most ordered form, waiting in the darkness for a world to gather it in. In the vast, cold nurseries of new worlds, water freezes. But not all ice is created equal. One form possesses a regular, ordered molecular structure, a crystal lattice identical to the ice in our freezers. It stands in stark contrast to its chaotic cousin, amorphous ice, where water molecules are frozen in a state of disarray. The discovery of this crystalline ice, within the swirling disk of gas and dust around a distant star, is a profound clue. Its very existence speaks of specific conditions, of a precise balance of temperature and pressure found only in the frigid outer realms, far from the star's warmth. Peering into the infrared, the James Webb Space Telescope captured a spectral fingerprint, distinctive features of light absorbed at specific wavelengths. The signal was unambiguous. It was the signature of crystalline water ice. Here, in the very region where giant planets are thought to be born, lies an immense reservoir of frozen water. This is not merely a chemical curiosity. It is a discovery that touches upon the deepest questions of existence. Water is the crucible of life as we know it. Worlds born in the fire of the inner disk begin their lives barren and dry, baked by temperatures far too high for ice to survive. Their water must be delivered later, a cosmic migration of comets and asteroids forged in the outer disk, carrying their frozen cargo inward. The ice detected by Webb is that primordial reservoir, the wellspring that could one day seed inner rocky worlds with oceans. The giants of a solar system also depend on this ice. Our best models of creation sieve enough to gravitationally ensnare the primordial hydrogen and helium gas that surrounded them. These cores were built through the slow, violent accumulation of icy planetesimals, solid bodies ranging from meters to hundreds of kilometers across. The abundant ice revealed by Webb provides the exact raw material needed for this colossal construction. Even the structure of the ice tells a story of the disk's history. Amorphous ice is the product of haste, formed when water vapor freezes in an instant. Crystalline ice requires a more patient process, either a slow, deliberate freezing or a later period of warming that allows the molecules to find their place, to arrange themselves into a perfect, repeating pattern. To find it here suggests the disk has been thermally processed, its chemistry altered by shock waves or the gentle, persistent radiation from its infant star. The star at the center of this observation is a sibling to our own sun, making these findings a direct window into our own deep past. If such vast quantities of ice were present in our own solar nebula, then the process Webb now observes may be a mirror, reflecting the very events that unfolded here 4.6 billion years ago. And this is not an isolated case. As Webb turns its gaze to other stellar cradles, it finds similar features. Crystalline water ice, it seems, is a common ingredient in the recipe for planets. This suggests that most nascent systems have access to substantial amounts of water during their formation, dramatically increasing the probability that rocky worlds, orbiting in the gentle warmth of a habitable zone, could acquire the one substance essential for life's genesis. Yet, it is a delicate balance. The amount of ice matters as much as its presence. Too little, and giant planets may never form, robbing a system of its gravitational shepherds. Too much, and the disk might shatter into a multitude of competing cores. As we measure the ice in system after system, we begin to understand the cosmic calculus that determines not only if a world is born, but if it is born with the potential for a future. In these frozen crystals, scattered across the galaxy, we see the architecture of possibility itself. Beyond the familiar frost of water, the frigid outer darkness of a stellar nursery holds a more exotic chemistry. Here, carbon dioxide, methane, and ammonia crystallize into cosmic dust, substances that freeze solid in the deep cold. The piercing infrared gaze of the Webb telescope has found them, tracing these frozen compounds in the swirling disks where new worlds are born. This primordial mix of ices is a recipe for destiny. The final composition of a planet is dictated by the materials from which it coalesces. A world forming from this ice-rich slurry will have a profoundly different character than one born from simple rock and dust. In these observations, a direct line is drawn, from the cradle of a star to the formation of its planets to the very foundations of astrobiology. The ices locked in these disks are the raw ingredients available for construction. The planets that emerge are a direct inheritance of this cosmic chemistry. From this frozen inheritance, rocky worlds in the habitable zone might one day acquire water, atmospheres, and the complex organic compounds that are the precursors to biology. Some, perhaps, might eventually awaken with life. Webb is conducting a grand inventory, cataloging these ingredients across a vast census of stellar systems. By the end of its mission, astronomers will possess a statistical map, a new understanding of how common these planetary recipes are. This knowledge will reshape our theories of creation and help predict the kinds of worlds that populate our galaxy. Yet, as the telescope witnesses the quiet genesis of new systems, it also bears witness to the violent death of the old. The flash was ephemeral, lasting just 8 seconds. In that fleeting moment, a single dying star unleashed more energy than our own sun will emit over its entire 10 billion-year lifetime. The explosion launched jets of matter outward at 99.99% of the speed of light. And when one of these incandescent spears pointed directly at Earth, detectors across our world registered the ghost of its passage. This was a message from the dawn of time. The gamma rays had traveled for more than 13 billion years to reach us. By the time Webb turned to observe the fading afterglow, the explosion itself was already an echo of ancient history. But in that echo were the details of stellar death in the first billion years of the universe. These gamma-ray bursts are not all alike. Short bursts, lasting less than 2 seconds, are the signature of colliding neutron star in origin, the cataclysmic collapse of a single, massive star. The mechanism is one of ultimate failure. When a star more than 20 times heavier than our Sun exhausts its nuclear fuel, the core can no longer fight the relentless crush of its own gravity. It implodes, collapsing into a black hole. As surrounding material screams inward, it forms a spinning accretion disk. Powerful magnetic fields, threaded through this disk, erupt, launching twin jets that punch through the collapsing star and emerge into space at relativistic speeds. The sheer energy heats the material to billions of degrees, unleashing a torrent of gamma rays. As the jet thunders outward, it plows through the surrounding medium, creating a shockwave that radiates across the entire electromagnetic spectrum. It is a final, furious announcement of a star's demise. In this cosmic ledger, however, destruction is merely a prelude. The death of one star seeds the void with the elements required for the next generation of suns and worlds, a cycle of unimaginable violence and quiet creation, forever turning in the deep. Across the unfathomable gulf of space and time, the James Webb Space Telescope turned its gaze toward a fleeting whisper of light, the afterglow of a cosmic cataclysm. Its instruments dissected this ancient signal, wavelength by wavelength, revealing a story written in the heart of a dying star. Within the infrared spectrum, a chemical fingerprint emerged. Ghostly emission lines betrayed the presence of heavy elements: silicon, oxygen, iron. These were not primordial materials forged in the Big Bang, but the intricate creations of a stellar furnace. Forged through the immense pressures of nuclear fusion, they were violently cast out into the void during the star's final, explosive moments. Webb was performing a cosmic autopsy, analyzing the very innards of a star splayed across the heavens. The discovery, while seemingly intuitive, was a profound confirmation. It was never guaranteed that the universe's first, most metal-poor stars would die in the same manner as their modern descendants. They might have collapsed differently, perhaps producing fewer of the elements essential for life. Yet here, in this echo from the dawn of time, the signature of enrichment was strikingly familiar. It suggests the fundamental physics of creation and destruction has remained a constant, an unwavering law across cosmic eons. But the burst was more than a death notice. It was a beacon. As its light blazed across billions of years, it journeyed through the tenuous, invisible gas of the intergalactic medium. This primordial fog absorbed specific wavelengths, leaving its own dark, telltale imprints upon the spectrum. By reading these absorption lines, astronomers can now probe the composition of the universe when it was just a fraction of its current age. The observations revealed the shadow of neutral hydrogen, a critical clue. It tells us this explosion occurred during, or just at the close of, the epoch of reionization, that pivotal era when the first starlight burned through the universe's opaque, neutral fog. Along this specific line of sight, pockets of that primordial darkness still remained. With each new gamma-ray burst observed, another sightline is drawn, mapping the patchy, uneven nature of this cosmic dawn. Such events are impossibly rare, perhaps only one per galaxy every million years. Yet, in the observable universe, a theater of countless galaxies, hundreds occur every single day. The challenge is not their existence, but the race against time. Ground-based sentinels can alert Webb within minutes of a detection, triggering a cascade of rapid response observations. The telescope must pivot, interrupting its scheduled work to capture these transient phantoms. For a gamma-ray burst, speed is everything. The afterglow is a brilliant but ephemeral spectacle, fading to undetectable levels within mere days. To capture meaningful data, Webb must be on target within hours. Each successful observation adds another crucial piece to the mosaic of the early cosmos. As the sample grows, from a handful to dozens of distant bursts, statistical clarity will emerge. We will see not just how one star died, but how the very first generation of massive stars lived, how they seeded the void with the elements of future worlds, and how their violent deaths triggered the birth of all that followed. The frontier, however, is always moving. Every few months, a new distance record is announced, a new galaxy found shimmering even closer to the beginning. Each one is a step further back, a page turned closer to the opening sentence of the cosmic story. We are pushing ever deeper, peering past the first stars, toward the edge of darkness itself. With every observation, the veil is pulled further back, revealing the universe in its infancy. We are witnesses to a relentless push into the dawn of time itself. For a few months, a distant smudge of light, a galaxy at a redshift of 14.32, held the title of the most ancient object ever seen. Then, the record fell. Another was confirmed, slightly deeper in the cosmic past, at a redshift of 14.5. The chase continued. Not long after, a new candidate emerged, a ghost of a galaxy shimmering at a proposed redshift of 16. Spectroscopic confirmation is still pending, but if its distance is proven, we are seeing light that has traveled since the universe was a mere 250 million years old. The question echoes through the halls of astronomy. Why does the frontier recede so quickly? Part of the answer lies in the youth of the instrument itself. Astronomers are still sifting through the torrent of data from Webb's first years, a treasure trove of cosmic secrets. As they meticulously work through these initial observations, ever fainter, ever more distant objects are coaxed from the darkness. The deepest images, the most profound glimpses into the past, require tens of hours of exposure, a patient, unblinking stare into the void. Not all deep fields have yet been targeted. More are scheduled. But it is not just the hardware. Human ingenuity is evolving alongside the technology. Analysis techniques sharpen as scientists gain an intimate familiarity with the telescope's data. Sophisticated machine learning algorithms now scan the vast digital canvases, flagging potential high redshift candidates that a human eye might overlook. Each candidate is then subjected to the rigorous teint, confirming or refuting the whispers from the edge of time. There is also a sense of statistical inevitability. If bright galaxies could form at a redshift of 14, it stands to reason that even brighter, more prominent ones could exist slightly earlier, at a redshift of 15. The formation of galaxies was a continuous process, and the very first are simply the rarest. If one searches a large enough volume of space, the cosmic lottery dictates that they will eventually be found, and Webb is searching that volume. This cosmic archaeology, however, cannot go on forever. Eventually, we will reach a wall. We will arrive at the epoch of the very first stars, an era before which there was nothing to see. Before a redshift of 20 or so, the universe was a different place, a place without light. It was an age of darkness, filled only with a fog of neutral hydrogen. Webb may one day detect the faintest whisper of emission from this primordial gas, but it will not find galaxies there, for none had yet been born. Between the known frontier at redshift 14 and the ultimate wall near redshift 20 lies the great unexplored territory. Theory predicts the first galaxies should ignite by redshift 15 or 16. The gap between that prediction and our direct observation is now narrowing with every new discovery. Within the next few years, it is almost certain that Webb will find them, extending our vision to encompass 98% of all cosmic history. Each record-breaking discovery is more than a number. It is a lesson. Its brightness reveals the ferocity of its star formation. Its spectrum betrays its chemical composition, the first hints of heavy elements forged in the hearts of stars. Its size offers clues to how the grand cosmic structures we see today began to assemble. Together, these measurements are the crucible in which our models of galaxy formation are tested. Each new data point either confirms our understanding or forces a profound revision. Some of these ancient galaxies appear surprisingly familiar, forming stars, containing traces of heavier elements, their sizes consistent with our theories. But others are extreme outliers. They are too bright, too massive, too chemically enriched to exist so early. These are the anomalies that excite us most, for they challenge the very foundations of our cosmic story. They hint at a physics we do not yet fully grasp. In this relentless pursuit of the first light, we are not merely cataloging the distant past. We are piecing together our own ultimate origin story, tracing the long chain of events that led from a dark, simple universe to the brilliant complexity of our own existence. The search is not for a record, but for an answer to the most fundamental of all questions. How did it all begin? To gaze upon the light from the dawn of creation is to touch the intangible. Within these images, galaxies born in the first few 100 million years of existence render the abstract sweep of cosmic history into something we can see, something we can feel. Each photon is a traveler, an ancient messenger that has journeyed for 13 billion years, ending its pilgrimage in our eyes. But behind the breathtaking vistas and the records of cosmic distance, a far deeper and more unsettling mystery unfolds. The universe is not merely expanding, it is accelerating. The great cosmic tapestry is being stretched apart, with galaxies rushing away from each other faster today than they did billions of years ago. An unseen, unknown force is driving space itself to swell with ever-increasing strength. Astronomers have given this phantom a name: dark energy. Its discovery in the late 1990s was a revolution. The key was found in the death throes of distant stars, supernovae, acting as standard candles across the cosmos. By measuring the apparent brightness of these cataclysmic explosions, scientists could calculate their distance. When they compared that distance to the star's redshift, a measure of how fast it was receding, the numbers revealed a shocking truth. The expansion was not slowing down as expected, it was speeding up. For the first several billion years of its life, the universe was locked in a tug-of-war. Gravity, the familiar force pulling all matter together, acted as a brake, slowing the initial outward rush of the Big Bang. But then, approximately 6 billion years ago, a tipping point was reached. Dark energy, a force once negligible, began its inexorable rise to dominance. The cosmic brakes failed, and the accelerator was pressed to the floor. Today, advanced instruments peer deeper into this enigma. Observations from the Webb Telescope confirm and sharpen this strange history, studying supernovae at ever greater redshifts, extending our measurements further back toward the beginning. The data is unambiguous. For billions of years, this acceleration has been a constant feature of our reality. But what is dark energy? The honest answer is that no one knows. The most elegant explanation is woven into the very fabric of existence. It suggests that dark energy is not a substance floating in space, but an intrinsic property of space itself, an energy of the vacuum. Albert Einstein's equations of general relativity permit such a thing, a cosmological constant, an energy density that remains unchanged even as the universe expands. This leads to a staggering paradox. As the cosmos grows, more space is created. And if energy is a property of space, then more energy is also created. The total sum of dark energy in the universe is increasing, driving the expansion ever faster. This appears to shatter one of the most fundamental laws of physics, the conservation of energy. Yet, in the warped and dynamic arena of general relativity, the rules are different. The expansion of space-time itself can generate energy from nothing, without violating the mathematics that govern it. To measure the nature of this force is now one of the highest goals of modern cosmology. Is it truly a constant, as Einstein's simplest model suggests, or does it fluctuate, changing its strength over cosmic epochs? Each data point, captured from a different era of the universe, helps constrain the possibilities. So far, all measurements suggest that dark energy has been remarkably, stubbornly constant. Its density does not appear to have changed as the universe has aged. This result fits the simplest theory, yet it explains nothing. To say it is a cosmological constant is merely to give a name to our ignorance. It is an answer that leaves us with the most profound question of all. Why is there a value to this constant, and not simply zero? We have found a ghost in the machine of the cosmos, a force that dictates the ultimate fate of everything, born from the emptiness of space itself. And we are left to wonder not just at what it is, but why it is at all. Its fundamental nature remains a profound enigma. Alternative theories whisper that this dark energy is not a constant, not an immutable property of space, but a phantom in flux, a dynamic field that evolves across the cosmic ages. Some models predict it was stronger or weaker in the universe's youth. The deep field measurements from the James Webb Space Telescope are our test for these predictions. But so far, the data reveals no clear deviation. The constant holds. Upon the true nature of this force, the entire future of existence depends. If it remains as it is, a constant, the expansion will accelerate forever. Galaxies beyond our local family will recede, gathering speed, until they are swept away from us faster than the speed of light itself. One by one, they will slip beyond a cosmic horizon, their light never to reach us again. They will vanish, leaving our descendants in a universe that grows ever darker, emptier, a cosmos of deepening silence and cold. But what if dark energy increases? The acceleration could become so extreme, so violent, that it would not merely push galaxies apart, but shred the very fabric of existence. In a scenario known as the Big Rip, the force would overwhelm gravity, tearing apart the great cosmic structures, galaxies, stars, planets, and finally, the atoms that form us, would be ripped asunder. Current measurements give no indication of this cataclysm, but the possibility, however remote, remains. And if dark energy weakens, if it fades over the coming eons, gravity would once again become the master of the cosmos. The expansion would slow, halt, and then reverse. All of creation would be pulled back together in a great cosmic inhalation, a big crunch. The universe would collapse into a final, fiery singularity, perhaps to be reborn in the crucible of another Big Bang. A cyclical, eternal cosmos, a theory for which we currently have no evidence. To distinguish between these ultimate fates, Webb charts the expansion of spacetime across different epochs. Its precise measurements, woven together with data from across the world, will one day reveal the truth of dark energy, whether it is a constant or a force in motion. It is one of the deepest questions in all of science. And yet, even for this monumental instrument, there are shadows it cannot pierce. There are limits. Some objects are too faint, some too distant. Some radiate in wavelengths forever beyond its gaze. The first 200 million years after the Big Bang remain a ghost story, a chapter of cosmic genesis just beyond the edge of what Webb can reach. Galaxies from this earliest epoch would be stretched to a redshift greater than 20, their light so attenuated, so shifted to the far infrared, that even Webb strains to hear their whisper. They would be small, nascent things, having had little time to ignite their first stars. To see them would require impossibly long exposures, and perhaps the aid of a gravitational lens, an entire galaxy cluster bending space-time, acting as nature's own telescope. Webb has the technical power to find a galaxy at redshift 20, but only if it is bright enough to be seen. The simulations of that era, however, paint a different picture. They tell of the first galaxies being mere seeds, with the mass of only a few million suns. Such primordial embers would be far too faint, their ancient light lost in the abyss, invisible even to the most powerful eye humanity has ever opened to the sky. For all our ambition, for all our technology, we are reminded that every horizon we reach reveals another, more distant shore. The universe does not give up its deepest secrets easily. Perhaps the ultimate truth is not found in the answers we find, but in the relentless, unyielding quest to look deeper into the darkness, forever searching for the light of the beginning. There is, however, a tantalizing possibility. If the first galaxies ignited their stars with an efficiency far beyond what our models predict, they might just burn bright enough to pierce the cosmic gloom. This is not mere speculation. Throughout its mission, Webb has found that early galaxies have consistently been more luminous than expected. If that trend holds, stretching back into the deepest shadows of time, then galaxies at a redshift of 20 might be within our grasp after all. But this cosmic archaeology is fraught with deception. At such extreme distances, the universe is a hall of mirrors, where telling a true primordial galaxy from a foreground imposter becomes an immense challenge. Certain cool, dim stars within our own Milky Way can perfectly mimic the colors of the most distant objects we seek, celestial masquerades that can lead astronomers astray. The truth can be unveiled through spectroscopy, the science of dissecting light. But to capture a spectrum from the faintest, most ancient candidates requires an astonishing investment of time on the world's most powerful instrument. The James Webb Telescope is slated to operate for at least 10 years, perhaps longer, should its fuel and instruments hold. Throughout its life, it will execute ever deeper stares into the abyss, pushing the frontier closer and closer to the epoch of the very first stars. Future observatories may one day peer beyond Webb's formidable reach, but for now, it alone stands on the edge of cosmic dawn. What could possibly surpass this monumental machine? On the ground, titans of glass and steel are rising, enormous telescopes armed with adaptive optics, granting them superior light-gathering power in certain wavelengths. Yet they remain shackled to our planet. Earth's atmosphere, the very air we breathe, is a shroud, absorbing the precious infrared light from the farthest shores of the universe. For the most ancient galaxies, space remains the only true vantage point. The next generation of great space observatories is still the stuff of dreams and designs. Concepts envision mirrors twice the diameter of Webb's, or vast arrays of telescopes flying in formation, their combined vision extending our sight to a redshift of 25 and beyond, perhaps to witness the birth of a solitary, first-generation star. But these instruments will not leave Earth for decades. We need not wait for a revolution. It is happening now. Every observation from Webb seems to reveal something unexpected. Black holes, impossibly massive for their galactic cradles. Galaxies, blazing with a brilliance that defies their tender age. Star formation, proceeding by a rule book we have yet to write. Structures, emerging from the cosmic dark far sooner than our theories allowed. These discoveries do not shatter cosmology, they expand it. They reveal that our models were too simple, our predictions too conservative. The universe is proving to be richer, more complex, and more surprising than we ever dared to imagine. Webb is showing us the reality, and our theories must now race to catch up. We are living through a golden age of discovery. Never before has humanity witnessed the early universe with such clarity. Never before have we watched the assembly of galaxies just moments after the Big Bang. Never before have we probed the death of stars billions of light years away, or peered into the churning hearts of distant stellar nurseries. James Webb has pulled back the curtain on the true scale of existence, revealing a cosmos vaster, stranger, and more magnificent than anyone had ever predicted. With every captured photon, a long-held certainty crumbles. Each new vista revealed challenges the very foundations of what we thought we understood. The cosmos, it seems, is not yet finished revealing its secrets. Our silent sentinel in the dark continues its vigil, pushing ever deeper into the twin abysses of time and space, unveiling wonders not merely unseen, but previously unimagined. This is not the end of the story. It is the first, breathtaking sentence of an entirely new chapter. A window has been opened to the cosmic dawn, and through it, we gaze upon the infancy of everything. We are a species only now learning to read the language of this ancient light. For 13.8 billion years, the universe expanded in magnificent, silent solitude, waiting for a consciousness to evolve and look back. Now, finally, we are looking, peering into the crucible of creation, to the very edge of time itself.